There was one errata in the input output characteristic graph that we draw in the I versus V graph. Till you cross the barrier potential, the current will be 0, right? And when you are about to reach the barrier potential, there will be some current. So this barrier potential, this point is called the NEE. So in the last lecture, erroneously, I told this is NEE, right? So this is called the breakdown voltage or Zener breakdown. So in the forward biased, we have NEE, you can say NEE voltage. And this is the Zener breakdown. Okay, this is the reverse bias case. So that was only difference. Okay, what I said that the left side I said as NEE also, which is wrong. Okay, so let's make a change. Okay, the rest is simple. So we have done the diode as a rectifier as well, right? And also the efficiency of a half wave and full wave rectifier, isn't it? We have done all this.
Yeah.
So now the next part is called the transistor. I think we can also do one more thing that's called the optoelectronic devices. There are three famous optoelectronic devices. The first is called the LED, light emitting diodes. Second is
Light sensitive resistance.
that is not, it's like a, yeah, you can say, but this is called photodiode. To measure the intensity of light. So this is the light emitting diode, right? This we use for the measurement of intensity of light. And the third is solar cell. Okay, so here we receive the light and we develop the potential. Okay, so solar cell is the inverse process of LED. Yes. So in LED, what happens? An electron combines with a hole, and as a result of a recombination, it releases certain amount of energy, and that energy is emitted in form of photon of a given wavelength. So that is your LED. But in photodiode, in solar cell, it's a reverse process. What you do is you receive light, correct? You receive light, and as a result, what happens? In solar cell, you receive light, and then what you do? You break the bond and create the electron hole pair. And these pairs are separated, and hence we create a potential difference. So that's why it's a inverse phenomenon. Okay. In photodiode, what you do? we receive light. Okay, there also we receive light, and we keep a PN junction diode biased, so it is going to be reverse biased, and as a result, when light will fall, then it will again create the electron hole pair, and that creation of the electron hole pair will create the reverse saturation current. So in a way, for a given intensity, you will get a different reverse saturation current. So we'll see one by one. So let's begin with LED. So in LED, first of all, you need to remember three things. LED, we use forward bias. So an LED is basically a forward biased PN junction diode. What is photodiode? It is a reverse biased PN junction diode. And what is solar cell? Any guess? If one is forward and other is reverse, so the solar cell will be unbiased. Interesting. So there is no biasness. We don't use any biasing in case of solar cell. So the basic difference is this: LED forward biased, photodiode reverse bias, solar cell unbiased. That's very simple. Okay, how it works, let's see one by one. And you're not supposed to think much. So we have a notation for all. Notation. I'll just go one by one. So for LED, the notation is you take the diode and LED will emit the light. So draw some arrows like this. That's it. Simple. So how to represent the photodiode? Take the LED.
Reverse
and in
arrows.
case of photodiode, light will
Fall on the diode.
come. So it's like just change the notation, and that's it. So for solar cell, nothing. There's nothing. So there is no symbol actually. Solar cell. So we don't have any particular symbol for it. Now we'll see how we design. So if you remember the sequence, LED means forward bias PN junction. In photodiode we have the reverse bias. In solar cell we have unbiased. There is no biasness at all. So that's why I'm writing in sequence, and we'll also study in sequence. Next part. What is the functioning of a LED? So first of all, you have to draw a PN junction. So draw a PN junction, P type, N type, and the overlapping region is the depletion region, we can say, right? So this is like a depletion region. And what do you do here? This is N type. Because it is LED, so we must make a forward bias. So the biasing will be, the P will be at high potential and N will be at low potential, correct? So just do a cell. And the rule is simple: the potential of the cell must be more than barrier potential, then
Break.
only it will operate.
Yes.
Otherwise, it will not operate, right? Sorry. So now P type will have the excess of hole. So hole will try to go this way and electron will try to go this way. So the current in the forward bias PN junction, the current I is due to holes as well as electrons. Always remember that in a in a forward bias case, we have a current due to both. Okay, so the holes and electron both create. So what happens when they enter? They recombine, they meet together, and this is again the process called annihilation. And as a result of a recombination process, so a recombination of electron and hole annihilate and A double N, I think.
HILATE.
Annihilate each other and releases energy. Okay. Okay. So now what we need to know or remember here is one simple relation. And what is the simple relation? So there is a energy. If you remember the bond, this energy diagram, do you remember? In the very beginning, I drew the energy diagram. So in a PN junction diode, we have the conduction band and the I hope you remember this diagram. And this is called the
Yes.
energy gap. This is called the energy gap, which is the gap between the conduction band and valence band. So whenever there is a recombination, okay, then the energy release is as per the energy gap. So they may ask you that if it will undergo the, you can just do like this. So from this surface, it will start emitting a particular wavelength of value, let's say frequency is mu. Then the energy release will be as per the energy gap between the conduction band and valence band. So there is a transition. You can say this is because see, a recombination process means you go back to the bond position. I mean, you become a bond. So whenever this happens, it is like this electron will jump from here, okay, and combine with the hole here. So hole is a part of valence band and electron is a part of conduction band, and as a result, and always remember one thing, that in conduction band we have I, in the valence band we have IH. Okay, so in a circuit both bands are, of course, in a material medium it is same, but energy wise there are two types of current, and the whole current is a part of valence band and the electron current is a part of conduction band, if you talk about in terms of energy. So whenever there's a transition from the conduction band towards the valence band, this recombination is equivalent of this energy gap. It's like a if you compare with the Bohr's theory, There is a transition from the high energy conduction band to the low energy valence band, and this difference is released as photon. So the equation that you will be using in order to solve question is Eg equals to He. I hope this is clear. And they may ask you
Yes.
that, okay, if I increase the doping, what will be the effect on the frequency? So we know that doping will decrease the gap. So with increase of doping, if you remember, doping always diminishes the energy gap either by lowering the conduction band or increasing the valence band.
Yes.
If you remember, there is about something like effect of doping on the energy gap, right? So with increase of doping, Eg will decrease, hence frequency of release photon will always decrease, or you can say wavelength will increase, right? So you can also write Eg equals to Sc by lambda. So they may ask you find the lambda, Sc by Eg. So what they will ask you, only question from this, okay, the lambda question, okay. Nothing else they will ask. There is no graph you're supposed to remember, that this is the simple thing, okay. So LED is clear. Any doubt in LED? Tell me, guys. Hello.
No, sir.
Okay. Next part. Quickly, we'll go quickly. So the bare minimum which you need to remember, just remember, that's it. After LED, what is next? Photodiode. In case of photodiode, see, let me tell you, the light again is energy. So whenever light is incident on a diode, it simply breaks the bond and creates electron hole pair, nothing else. Now, the rate at which it generates the electron hole pair is very, very low. So the kind of current it can create by breaking the bond is of the order of microampere. Now imagine if you have a photo p-n junction diode, I mean, sorry, if it is a p-n junction diode which is forward bias, and then light is falling. So it is quite possible that apart from the forward current, the light may create some extra current. But in a forward bias p-n junction, what we know, the current is of the order of milliampere, and the light will create how much current? Of the order of microampere. So any change to milliampere current by microampere will be insignificant, or you can say difficult to detect the change, isn't it? And therefore, if you use a photodiode and if you try to use it in a forward bias junction, I mean configuration, the problem is we cannot see the change, and therefore we cannot understand the light intensity. So what we do is we use it in the reverse order, reverse bias in case. Why? Because in the reverse bias, we know the current itself is microampere, and the light can only produce the current of the order of microampere. So a change of microampere in a microampere will be significant and can be observed. Understood what I'm saying? Tell me, guys, is this clear?
Yes, sir.
So what exactly happens if you try to again draw the, first of all, okay, I have written this. This is used in the reverse biased case. So if you have this p-n junction, and if you make a connection like this, So you can see that we have connected the P type with low potential and N type with high potential. So this is low, this is high. And this is the reverse bias voltage, whatever be. And here, as a result of this, so always remember on the N side, you have a depletion of positive charge. On the P side, we always have a depletion of negative charge, right? I hope you remember this. A P type here will have how much layer? The depletion layer will have negative charge, right?
Negative.
Because P type will have a negative charge with hole, and N type will have a positive charge with
Or the
electron.
fixed charge and electrons. Yeah.
So when you deplete, you will get a negative. So P type always have a negative potential. So the potential is negative, and it is like if you draw a potential, it goes this way. Okay. I should have drawn a better way. But anyway, the potential graph will be, so positive charge means positive potential, negative charge means negative potential. Anyway, the idea is this: in photodiode, what is coming here? So we create a transparent base. So the base must be, the depletion region must be. So we make sure that the depletion region is transparent for the light to come. And the rule is the depletion region should be reachable by the light. So when the light will come to the depletion region, you can think the other way around. It is H nu, and what it will do? It will break the bond. Understood? In a way, this energy will be received by the electron, hole in the valence band, and will jump to the, or you cannot not say electron, the electron in the valence band will jump to the conduction band. So if I do the energy diagram, how it look like? The energy diagram of the photodiode. Just do this. Again, we have the energy gap. It is just a reverse process. So the electron in the conduction band, this is valence band. So you supply the energy, and the energy is sufficient to pull this here. So it's a reverse process. You receive the energy, and if the energy is, so here the rule is what? The incident energy must be more than energy gap.
Yeah.
So there are some logical thing which you should be concerning here, that because generally if you are using the white light, okay, so we take the value of yellow green region, which is roughly 5500 angstrom. So for white light, if you're using white light for some reason, then we use lambda in the range of yellow green region, and the value we roughly take as 5500 angstrom. And so the energy of such a light, so energy value is how much? SC by lambda, which is 12400 angstrom EV, right?
Yeah.
Upon 5500 angstrom. So how much is the energy, guys? This is roughly. Anyway, let me just calculate. It is 2.25, right? And of course, this energy is less than the energy gap, because in case of semiconductor, the energy gap is, if you remember, it's less than 3 volt, right?
Yes.
So this is any less than 3 volt. Actually, this is EV. So generally what they ask is, okay, how much energy you must supply to this electron to jump. So the answer is this energy should be more than the energy gap. Okay. And now you can see the energy gap we have to keep very small. How small we have to keep the energy gap? The energy gap should be less than 2.25 electron volt, right?
Yeah.
So you need to keep a very small energy gap, and this is achieved by the highly doped PN junction diode in a reverse biasing. Okay. So this is the highly doped, because as the doping will grow, we know the energy gap will decrease. Okay. So the rule is simple. In case of photodiode, it is a reverse process. H nu is sufficient to drag the electron from where to where? Valence band to which band?
Conduction.
Conduction band. And in the case of LED, what is happening? You can see what is happening here.
Electron jumps from conduction to valence.
So just remember this fact. Okay. Now, one more thing they will ask you the graph. Because we are using the reverse biasing of the PN junction. So in the reverse bias, what happens? We will have a reverse saturation current, right? So the IV characteristic we can draw. How it will look like? Something like this.
Yes.
Now, as you increase the intensity, what will happen? The reverse saturation current will grow in value. So they may give you graph like this, and I1, I2 and I3 are intensity of light. Reverse saturation current, biasing voltage. This will be in microampere. So as you can see clearly, as the intensity will grow of the light, it will also increase the reverse saturation current. So you can tell me clearly which intensity is maximum. So I3 is maximum, right?
Yes.
For the obvious reason. Okay. So what is left now? Solar cell, right?
Then how does an LDR work? Is it similar to this? Or?
LDR should work in the same fashion. I mean, let me read about LDR. I haven't read. I mean, I have read, but it's a long time back, 20 years back. LDR actually increases the resistance only, no? Depending on the light, or decreases the resistance. I think it should be either forward bias or reverse bias.
It decreases as far as I know.
It is the same thing. When light strikes its surface, the material conductivity decreases. I think it's very contradictory. And the electron in the device valence band are stimulated to the conduction band. Then conductivity should increase.
Yes, sir. So resistance decreases.
So conductivity will increase, so resistance will decrease, but they have written conductivity decreases. I mean, as I can read.
Oh,
I mean, it's quite opposite. It's the same thing. Just let me read. It is like a photodiode only. So as I said, the street light uses the same thing. I know this is correct. Someone has written only. As the light ray will fall, conductivity will grow and resistance will decrease. That's simple. Okay. And the reason is same. What the reason? Exactly this reason. The incoming light will take the electron from valence band to the conduction band. So more the electron means lesser the resistivity.
yes.
Okay.
Yes.
So that's simple, I think. So you can also add LDR. What is LDR? Light dependent resistance. Light dependent. Now the last is interesting. Solar cell. So what exactly is solar cell? Again, it's a PN junction. It is PN junction, but when we create the solar cell with PN junction, we keep the P substrate very thin. So it's a PN junction. And what I'm saying, the P substrate means the material part. So you can think this way. If this is P type, the N will be much bigger, like this. Okay. And the reason is obvious why we need a very bigger N type, because we want large number of electrons. So the majority what we need is electrons. So a bigger N type will make sure that we have a large number of, electrons. But this is not the only reason. We have some more reason actually. So how exactly it works? Okay. So this is not a diagram. I mean, you have to draw a different way. I mean, not like this. So you have to draw a thin P layer. Just a very thin P layer. I think the thickness is roughly of the order of, I think, 30 micrometer. Hopefully this will be the value. Let me check. Anyway, we'll come to the thickness part. So for the sake of illustration, this is very thin. It's of 30 micrometer. And then the substrate of the N type is really thick. Now, what we need, the moment P and N type will come together, it will create a PN junction, correct? And therefore, you will have a depletion region, isn't it? So this region is the depletion region. Okay, so we have something like a depletion region. Okay. And in the depletion region, what you will have here? Negative charge. Correct? On the P side, we have negative, and on the N side, we have
Positive.
So what happens? This depletion region internally creates the electric field, as we know, in the direction like this. Correct? This is roughly the direction of electric field. I hope this is clear. So electric field will be from plus to minus.
Yes, sir.
Yeah, I think in the notes the student has made it wrong. I mean, the field they have done is other way around. Anyway, and dimension here is okay. This is roughly 3 micrometer, and this dimension is just a minute. And this is roughly of the order of 300 micrometer. Now there is a reason for this, why we keep the P layer really thin and the N layer so thick. The reason is we are going to receive light, correct? So we are going to receive light. And what we want? We don't want light to be coming to the surface. We want that light should be able to penetrate this layer. And after penetrating, it should reach the depletion region somehow. If you keep the thickness of the P substrate really thick, what will happen? The light ray will fail to reach. Now, what you should also know that every radiation for a given frequency will have some penetrating power. Understood? Will have some penetrating power. Okay. So generally, it is found that a high energetic photon will have a deeper penetration than low energetic photon. Okay. So we need to understand, okay, first of all, the first point, the reason for keeping the P substrate thin so that the incident light must reach the depletion region. Okay, so what we want, that it must reach the depletion region, and if it is reaching the depletion region, we are happy. Now if it is very high, I mean, now normally what happens, like if the wavelength is very high, it can really go deeper. If the wavelength is less, can only go to the surface. So we keep the thickness good enough so that majority of the light ray can reach the depletion region. And once it will reach the depletion region, this is similar to the photodiode. Now in the photodiode, we have reverse saturation current, we have reverse biasing. Here there is no biasing. Okay. Now there's some more thing you need to know. First is something called contact. So to make the connection for the wiring and all, what we do here? We create a finger contact here. You know what is finger contact? Have you anyone seen finger contact? Finger contact. Okay, I'll show you how it looks like. And the base will have the full metallic contact. These are just for connections. This is the metallic contact. And this is called the finger contact. This is the side view. If you look from the top, if you look from this side, what you will see is this. So from the top, what you will see is this. I hope you can see the finger contact now.
Yes.
This is the finger contact. Okay. And what I have drawn is only the edges. What you're looking here is the edges, this edge. This edge I have shown in the actual picture. So now why we need finger contact? If I make complete contact, then light cannot reach, obviously. So we want light should reach here, right? So we keep a metallic connection with some gap. Okay. And we need metallic connection so that we can make a terminal. Okay. Okay. So the moment this energy will fall or reach the depletion, then this will create the electron hole pair. Because this light will break the bond, and as a result of breaking a bond, it creates a electron hole pair. Now tell me, as a result of electron hole pair, what will happen? How the electron will experience force? Let's say you have created one electron, one hole. So where the electron will move? Up or down?
Down, sir.
Very good. Because the field is, you can see upward, so the electron will move down. And how the hole will move?
Upwards.
Upwards.
Upwards. Okay. So you can clearly see that the upper layer is going to be positively charged, and the bottom will become negatively charged. So you can see that the light ray is coming continuously, and by the virtue of creation of the electron hole pair, it is always, the pulled towards the p and n type respectively, and therefore the p type will become positively charged and n type will become negatively charged. And as I said, the doping is very high, so this pair production will occur at a greater rate, and as the light intensity will grow, we can have more and more charge getting accumulated over the surface. Now, after a long time, we will have enough polarity, or you can say potential difference. And this potential difference is what we need to run the appliances, right? So whatever you appliance, you connect across it. So this will behave as a cell like this, correct? And this cell, so what will happen, as long as the light ray is falling continuously, the charge will accumulate like this, isn't it? So generally, when the solar cell is not into use, it is always used to charge a battery. So what you do is you connect a chargeable cell. Okay. So let's say we have some chargeable cell, and in parallel we connect the other appliance, maybe a bulb or whatever. So what happens, as long as if I'm not using for running your appliance, this potential will keep on charging the battery. Understood? So the rule is simple. With the help of solar cell, we always keep the battery charge. And once you want to put this into use, Okay, the battery, let's say the light ray, I mean, light is gone. So once you switch on, we kind of connect the other appliance in parallel. So if the light ray is coming all the time, battery will keep on charging also, as well as it will discharge through the lamp or appliances. So you can use this energy in that way. Okay. If you want to use solar cell for your household, there is one more circuit you have to connect. What is that circuit? A battery delivers which power? AC or DC? A battery delivers
DC.
DC. But in our household, what we use?
AC.
AC. So how to convert a DC into AC? We know rectifier converts AC into DC, correct?
Yes.
And what we want here?
DC.
Convert the DC into AC, because in household we can't use DC, right? So if it is a small appliance, let's say a fan or a motor separately, then you can use it. But in our household, we need AC. So what we do? We connect a circuit which is called inverter circuit. That's why the name is inverter. Inverter is a circuit, name of circuit actually. So inverter converts DC into AC. So if you connect inverter at home, you have a battery, large DC battery you have to buy first. And that DC battery is connected to the inverter circuit, which is further connected to the household main supply. So from the main supply of our household, we make a connection to the inverter. The inverter connects to the cell. So when inverter is not in use, it will take the AC, and this AC inverter will have, I think, both circuit. They also have rectifier. So they take the household supply, charges the battery. That's called the rectifier process. When it is into use, it takes the energy from the battery and gives to the household by converting into AC. That's the inverter process or inverter circuit. So the box of the inverter will have both circuit, filter circuit and inverter circuit as well. So inverter is just a reverse process of rectifier. Okay. So I hope you have understood how this is working. The solar cell.
Yes.
Yes.
So what you're supposed to write? Should we write something here? Okay. I mean, this is very interesting question that preference of using of silicon gallium arsenide in solar cell. So the question is, if to break the bond by this energy, we should use technically what? We should use a depletion region with less barrier potential or less energy gap, isn't it?
Yes.
Okay, again, this is photodiode. In photodiode, what is the rule? The energy of incident photon should be more than energy gap. So
Yeah.
we tend to think that a lower energy gap will create better solar cell, because it is easier for light to break the bond and create the electron hole pair. This is what we think.
Yes.
But technically, this is not correct. Why? So there is a question in the NCERT why it is not correct. So a very small energy gap is not desirable for a better solar cell. So I'll put as a question actually. For solar cell functioning, the energy of the incident radiation should be more than energy gap. Then should we use PN junction with lesser Ag? So this is the lecture question. So what should be the answer? So as a fact, most preferable energy gap is 1.5 volt. This is most preferable. Now the question is why? Whereas energy gap of silicon is, I hope you remember, 0.7. And energy gap of germanium is how much?
0.3.
0.3. But though silicon is very less energy gap, so it's very easy to break the bond, isn't it? Germanium is even easier. But why we use something around 1.5, which is actually for the gallium arsenide? So most preferable is neither silicon nor germanium, rather the gallium arsenide. So the answer belongs to a concept of absorption spectrum. Absorption. So if you plot the graph of, the energy gap versus absorption, so it is found that the graph goes something like this, which means around this energy gap, the absorption of photon, incident photon is maximum. Now you may be wondering why. Imagine a photon is coming and the energy of photon is more than 0.7. It's a silicon. So that energy is sufficient to break the bond, yes or no? If I'm using the silicon PN junction, then the energy of the incident photon which we need is how much? Slightly more than 0.7, correct?
Yes.
But there is a problem, there is a catch. That light should reach the depletion region, but a lesser energy photon is absorbed on the top surface itself. That's the problem. It means although they have a the good good enough energy to break the bond, but they fail to reach the depletion region, they get absorbed on the surface itself. And that is like a problem. Understood what I'm saying? What is the problem? A less energetic photon cannot penetrate deeper. So they fail to reach the depletion. And what we need for the working of solar cell? We need that photon must reach the depletion region. So we want the electron hole pair generation in the depletion region, not at the top surface. Okay. So we can put it, this is answer. Since less EG means most of the photon will be absorbed by the surface. Hence, it will fail to reach the depletion region. And for better result, the EH pair production must occur in depletion region. So what does it mean? If you choose a larger value, then the photon with energy less than this will be anyway not used, and the energy of photon, if having more than this, it will not be stopped by the surface, it will reach the depletion. Because of the high penetration power, it cannot be stopped by the surface. So it will eventually reach the depletion and it will create the electron hole pair. So this is all about the solar cell. And gallium arsenide is most preferred. As a matter of fact, remember this. The last concept from the optoelectronic devices.
So
Yeah.
I didn't understand how the energy gap will relate to surface absorption, because surface absorption will depend on the wavelength of the light itself.
No. The thing is, let's say a large amount of photon is coming. Okay. A photon with a different energy absorption. I mean, different wavelength. So, of course, if when you are receiving the white light, are you receiving only one form of light or all components light? You're receiving probably all the components of light. Okay.
Yeah.
So what happens if one phenomena becomes dominant? Let's say if the energy of the incident ray is because the energy gap is very small, so they start coming. I mean, even those you can say photon with very less energy, they will be also start getting absorbed by the surface of the p-type only. Even the p-type starts absorbing such energy. Okay. And when the
How
p-type,
does that relate to the energy gap?
pardon,
How does that relate to the energy gap?
the energy gap is between the p-type and n-type.
Huh.
Okay. Now to create the pair of E and H, the photon should reach where? The depletion region.
Depletion region.
Now imagine the energy gap is very small. It's a very small. It's like you can think of 0.6, not 0.6, 0.7 for silicon. Then every photon can break it.
Yes.
Okay. So what happens when every photon can break it? Then it can occur near the upper end of the depletion.
Okay.
And if it is happening near the upper layer of the depletion, then those electron hole pair will not be thrown back to the N substrate. You can see N is here.
Okay.
I mean, unless we are not getting the electron here, it will not be pulled like this. If the electron is getting developed here, nothing will happen.
Okay.
Let's say somehow you are hitting here and you're creating the EH pair here. Then what is this EH will do? Nothing.
Nothing.
Because there is no field to be pulled left or right, up or down. So we have to make sure that this is not happening somewhere here. It is happening somewhere here.
Okay.
So we need a photon with a greater penetration power.
Okay.
And if we want photon with greater penetration power, it means other photon, I mean, should not create any EH pair elsewhere. So we need to go to depletion and we need a high energy photon which can have the better denting power or penetrating power. They reach there and they break it. Then it is thrown back into the p-type and n-type to create the polarity or the potential difference. So yeah.
And the electron hole pair which gets generated in the depletion region, why doesn't it first like shrink the depletion region?
No, depletion region, when you say the breaking of bond, so apart from all the depleted region or the layer, we further have some atoms. I mean, bond actually. Bond is, see, we show only few plus minus, right?
Yeah.
But we have infinite bonds, not one, you can't count it actually. So doping will create the depletion region, right? I mean, certain doping will have certain thickness of the depletion. The whole idea is if you have what you can say, what you ask?
I'd ask that why if the electron hole pairs which are created, why don't they first fulfill the deficiencies of the depletion region itself?
Because it is the moment it is created, it is pulled by the existing field. Okay. Because it's not a majority carrier. Only majority carrier which is coming from the P and N side can reduce the thickness of the depletion region. The charge which you create within the region is pulled back in the opposite direction as per the field only. Okay. And now the thing is, because of this contact, once it enters the electron enters the N side, and H enters the P side, it is eventually pulled and it is collected over the surface, the top surface, the metal. So eventually metal will collect. This is a highly doped region. So whatever you create will go here. Whatever you create here, electron will go at the bottom. So this, it is a property of substrate to maintain the electrical neutrality, if you remember, right?
Yeah.
I have taught this in somewhere in dipole itself. I mean, yeah. In dipole also what happens? The polarity is the end result, like the end surface. The bulk is always neutral.
Yeah.
The bulk is neutral because the electron hole pair will always have the, so it is like they hop till they go to the end point. So the electron entering the n type, n substrate will keep on moving till it becomes neutral again. And when it will become neutral, when it will reach the metallic junction.
Metallic. Yeah.
The same is for the above also, the p type also.
Okay.
Okay.
Yes.
Okay, this is just reason. The last thing that you should know is a graph, a simple graph. So how the graph is, the IV graph for solar cell, how it will look like. So in case of solar cell, what exactly you do is you create a plus charge. A minus. And from here you connect some sort of appliance. Let's say you connect a bulb. You have switch. Okay. So we have open circuit voltage. What we have? So open circuit will give you maximum voltage, isn't it?
Yes.
So open circuit. Okay. And short circuit gives you maximum current. So once you close it, you what will get? Maximum current. Short circuit current. Open circuit voltage. So these are two terminology which they use, VOC and ISC. And how we represent this graph? It's a simple graph. This is VOC. So when the voltage is open circuit, current will be 0. Okay.
Yes.
And when you short circuit, the voltage becomes 0 because it's a pure cell without any. So this is how we draw. This is called short circuit current. So when voltage across the terminal is going to 0, I mean PN junction, because you make it it is like you short circuit it. I mean there is no bulb, just a bat. I mean just a wire. If there's a resistance, then you will have some value. But imagine if you simply make the wire connection. So potential difference will be how much? Between this cell, okay, this just like this. If there is no resistor, if you only make the short circuit, what will happen? You will have maximum current.
Yeah.
But you will have no potential, 0 potential. Do you see this? IC implies VOC is, I mean, V is 0. Between these two terminals, what is the potential difference now? 0, no? No, not getting it. Potential, when you short circuit a circuit, I mean, any circuit, a battery, the potential difference we say it is 0 now. And current is maximum, isn't it?
Yes.
I mean, this is just a nomenclature. I mean, when there is a short circuit, I'm not showing this bulb. I'm saying if you short circuit, you will get the 0 voltage and maximum current. And if it is open circuit, then you will get the maximum voltage and 0 current. That's it. Like switch is open, switch is closed. Not getting it? Or think of a cell, any cell, common cell. What is the voltage now? same as the terminal potential difference, right?
Yeah, equal to EMF.
The EMF, so VOC is like EMF. But if I close the circuit, what is the voltage across? A closed circuit will give you 0, no?
Yeah.
Come on. If you
Yeah,
walk from A to B along the wire, what is the potential difference? 0 only.
Yeah, 0. Understood.
When you short circuit any battery, it is 0. But the current will be maximum at that instant, yes or no? So this is the graph. The voltage is maximum, current is maximum, and this is the graph. This is how it changes. That's it. So just remember this graph for the solar cell. Okay. So now we can move to the next big topic. What is the topic? So any doubt from the optoelectronic devices? Tell me, guys.
No, sir.
Let me show you some of the question of the previous year. Hopefully we should get. Okay. Let me show you. Can you see the screen now?
Yes, sir.
Yes, sir.
I'm searching for those questions. I think in the very beginning they asked those questions. But yeah, this is LED. A, B. So LED works in which biasing? Reverse or forward? LED will have which biasing?
Forward.
So which graph is for forward biasing? A, B, C, D. This. Which graph?
A.
That's it. A is the answer. Understood?
Yes, sir.
A is the answer, B is meaningless, C is meaningless, D is the reverse bias. So D is photodiode, right? Okay, let me see if I can get something more. Okay, no other question I can see. One more question. Just saw this question. Read the 26th question. A red LED emits light at 0.1 watt uniformly around it. The amplitude of electric field of the light at a distance of 1 meter from the diode is. Okay, this is what you can't answer as of now. This is from EM Web actually. It is solve this question. 23rd question. One, two, three, four. So 3 we just learned. 3 is for
Solar cell.
solar cell. And A
Fourth
one is for
Fourth
one
is
is for
LDR.
one is what? One is what?
One should be a diode, just normal diode.
Yeah, normal diode, LEDs. Okay. So option is okay. The third option should be solar cell, right? So check where is the solar cell third option.
C.
Yeah. Simple diode, Zener diode, solar cell, and light dependent resistance. So as the intensity will grow, the resistance will decrease. The fourth must be LDR. Correct?
Yeah.
Fourth graph is resistance between intensity of light. So fourth is LDR. So option is C. Which option? C is that option, I think. Correct? Hello, hello, hello.
Yes, sir. C.
Okay, okay. 30th question. Just check the 30th question. For LED to emit light in the visible region of electromagnetic light, it should have energy band gap in the range of which range? Common sense. There's no need to.
1.7 to 3.
Yeah, it is SC by lambda, and lambda will go from 3800 angstrom to 7800 angstrom, right?
Yes.
If you remember the range of the wavelength of white light, what is the range? Tell me, guys, what is the range of white light? Hmm? 3800 angstrom, right?
Yes, sir. From 2700.
And you can find the answer, I hope so. So definitely the answer gave what you're saying is correct. It will go from where to where? 1.7 to 3 electron volt, right? 76, I think.
Yeah.
Yeah. Anyway, this is the answer. Which other question we can solve? Just, I think this part we did, no? The GEE part. We have done all this question. Yeah. This is done. This is done. So from the optoelectronic device, questions will be really simple. Just be careful. Okay. Okay. Now they will not ask question like this. This is a very old question. Okay, we are very close now. We can go to the, yeah, this is done. So let's start the transistor. So our next topic is transistor. The word transistor has come from the concept called transfer of resistor, obviously a resistance. So we generally, okay, it's difficult to say as of now, but the purpose is to transfer the resistance, which we can also interpret in terms of transferring of voltage or transferring of current. So generally, we use transistor in a variety of reasons. So transistor can be used for the amplification of current or voltage. And transistor we can also use as a switch on and off. So it will act as a logic gate. You can switch on, you can switch off. Okay. So we'll see what is the on and what is off and what is the amplification you can say effect produced by the transistor. So to understand transistor, you have to understand again PN junction only. So a transistor is generally made with the sandwiching two PN junction. So how we make transistor? Is made by sandwiching two PN junction. Okay. So if I give you two PN junction, PN. So in how many ways we can sandwich? We can either join P to P together or N to N together, correct?
Yes, sir.
So if you join P to P together, what will get? When P and P will come together, then the P will become the center. So let's say the N of the first, the N of the second is here, and this is the P in between. So when you sandwich the two PN junctions such that the P is common, then what you get as a result of this combination is called NPN transistor. And transistor is how many terminal device? 2 or 3?
3.
3.
So every transistor is a 3 terminal device. Actually, you can think of it's a 4 terminal, 2 plus from 2 from here, 2 from here. But one terminal is common, so it will become 3 terminal device. You can see something interesting. I have drawn in a different sizes. Can you see different size? So what is the majority carrier of N type? Electron. And majority carrier of P type? Holes. Now, what we need to understand that when we create a transistor, then we keep a different doping concentration. So the part which you can see on the left, which is very small, is called the highly doped region. We call N plus. The symbolic notation of N plus is it is highly doped, and it is doped with N type. So we write N plus. That those are symbolic meaning to literature. So N plus means highly doped. But if you look on the N on the right, I haven't put a plus sign. What does it mean? Moderately doped. But if you look at the center, I write P minus. You know what is P minus? The doping of that side is less than even regular value. It's lightly doped. So I hope the first 3 terms are clear. The meaning of it. Now you can see that the one with maximum value of charge carrier will be the giver in the circuit. It will donate the charge to run the current in the circuit. And that is why the highly doped part is called emitter. And we write the symbol capitally. The moderately doped is having big size because it is the collector. It will collect all the charge. So you need a really big baggage to collect the large amount of charge coming to you free of cost. So this is called collector. So one is the donor, other is the receiver. Receiver must have the big baggage. I mean, you can store as much as possible. And the one which is in between, stuck between the two, is called
base.
base. So we have EBC. So these are some typical terminology. Okay. And this particular type of transistor we call NPN transistor. In most of the manufacturing, the NPN is widely used, and also in our syllabus we are going to deal with only NPN in most of the question. But if we do have the other way around, you can also create the similar thing by doing the reverse process. P N P. So this is called which transistor?
PN.
PNP.
So this is PNP transistor. Okay. Now this way of drawing the transistor is not convenient when it comes to circuit. So that's why we have a nice design. So how we represent what is the, you can say, circuit notation. So it's a very simple, you can draw a circle. You can draw a circle. So I'll draw here. Circuit notation. Circuit notation. So you can draw, first of all, a base. A base means any straight line. So you can draw a base like this or like this or like this, the way you want. It really doesn't matter. Okay, I'm drawing something like this. This is the base. Okay. And once you draw the base, draw a line from the base. Okay. Now this is the line also I have drawn. And then make a 3 terminal. One from the base, one from this line, and one from this line. Okay, which transistor is this? This is PNP. Correct?
Yes.
PNP. Now the flow of charge we always think from positive to negative, right? Current goes from where to where? Current
Positive.
goes from positive to negative. So you can put arrow either here or here. Choice is yours. So which one you will take, the upper or the lower? You can choose whatever you want.
Top, lower one.
Okay, lower only. The line with an arrow is called emitter. Why? Because the giver is emitter. Who
The
gives the
high-
charge? The
Emitter.
highly doped. So emitter is a giver. This is the emitter. And of course, if this is emitter, this is anyway base. Correct? Then this will become automatically collector. So you can draw like this. Similarly, how to draw the notation here? A circle, a base, 2 lines, and then 3 terminal. 1, 2, 3. Now, this is NPN. So current will flow from where to where? P to N. So I can draw the arrow like this. And once you draw the arrow like this, which one is emitter? Can you tell me which one is emitter?
Lower one.
The lower becomes emitter. This becomes,
Collector.
and this becomes base. Do you realize this? The notation is clear to all of you?
Yes.
Or is it difficult? Hasika, you understood this notation?
Yes, sir.
So once you have the notation, then we are ready to go with the biasing. Okay. So before we go for biasing, okay, I'll tell you why we do the biasing. Okay. The purpose of this transistor is that we take 2 terminal as input and 2 as output. Oh, sir, but we have only 3. How we can 2 as input and 2 as output? How it is possible to make a 2 pair as input and 2 pair as output? Simple. Take 1 as common, isn't it?
How?
In every transistor, we take 2 of them as input side and other 2 as output side. Is this clear?
Yes.
And one of the terminal will be common to input as well as output. So now we have 3 choices. We can keep common base, we can keep common emitter, we can keep common collector for the input and output circuit. So with the help of transistor, we create 2 separate loop or 2 separate circuit, you can see. So I'll draw it. So we have types of transistor configuration. Types of transistor configuration. Okay. So the first is called, the name is obvious, common base configuration. Second is called common emitter configuration. Third is called common collector configuration. See, the purpose of transistor is to create one input and one output terminal so that we can vary something in the input and we can get the response in the output side. And by doing so, we can achieve various tasks. So if you think a transistor as a switch, so you may switch on the left, it will switch on the right. So transistor generally act as the, you know what it act as? Transistor act as a NOT gate. You know what is NOT gate?
Yes.
A 0 makes 1 and 1 makes 0.
0.
Okay. So we'll learn that NOT gate property. It is simply NOT gate. So we'll see. Okay, first of all, this 3 configuration is obvious, right? Why we need 3 configuration? Because we have 3 terminal device. One must be common and one will become input, other becomes output. So how to draw all the 3? Generally, the common side we draw vertically downward. Okay. So if you want if you want to make the base common, then the base terminal must be like this. Yeah, that's correct. If you want to make the common common emitter, this must be common emitter. Common collector, this must be common collector. This is how we draw it. And once you draw this, draw a circle and then draw the base. Base is always like this. Then we have 2 arrows. I'm going to draw for the NPN type because it's easy. So in NPN, what we keep, if base is common, then we have 2 things left. What is left? Emitter and collector. So tell me, who should be input, emitter or collector?
Emitter.
Because it is going to give the current.
Yeah.
It is the source actually. And who is going to collect? Collector. That's the name. So emitter means N, P, N. And you want emitter on the left side. So the arrow must be like this. Because arrow is from P to N. Always remember this, easy to remember. Positive to negative. What is the direction of arrow? P to N. And the line with arrow is always emitter. A line without arrow is collector. This is just notation. No need to worry much. Okay. Then how we draw the circuit? So in every circuit, you have to do some biasing. Okay, when the giver can give, under which biasing? Can you guess? Which kind of biasing will allow the giver to give charge or current?
Forward.
Very good. So how to make the forward biasing here? Any guess? Forward biasing is only possible when N is at the low
Negative.
potential.
Yeah. Look.
You can draw like this. What this should be called, this battery? This is called bias voltage, right? You bias this voltage, right? So how we represent a bias voltage? Any guess? So again, there is a convention. To represent the bias voltage, we use double subscript notation. And the name of the input terminal, we can put it here. So V double E. What is the meaning of V double E? This is the voltage which is used to bias the input side. What is input side? Emitter side. Now every real diode will have some barrier potential, yes or no?
Yes.
Tell me guys, if something is, I mean, a forward bias, if it is PN junction, common sense. And if you forward bias, the barrier potential will be, this is VE, correct? So what is the barrier potential here? The barrier potential is always opposing, correct?
Yes.
Now, when it comes to transistor, the barrier potential we write as V EB. Which one is at high potential? The P side, no? So VB. The name will be what? This is high potential compared to E, correct? Isn't it?
Yeah.
If you look at the barrier potential, how it is? The battery is like this, no?
Yeah.
This is VB. But when it comes to transistor, the name will become VB. Why I'm writing B? Because B is at high potential and E is at low potential. This is called barrier potential. So this is how we represent, and this is what we mean by the different terminology here. So VEE and VBE, can they be equal? And answer, if the answer is yes, then under which condition? Think about it. See, don't think about the transistor, always think about the two PN junction. You'll get the answer easily. So if you think this is a PN junction, and if the input is forward bias, then how we must make the forward bias? You know
More than
it.
the barrier potential.
Yeah. So the VEE must be more than barrier potential.
Yeah.
So the rule is simple. The VEE must be more than barrier potential. And if it is more than barrier potential, then only a current will be flowing here, right?
Yeah.
So current will go here. Sorry. This is the current going here. What is the current value? The name is IE. So this current will be which current? IB. And this current will be IC. see, I'll come to this in detail actually. Okay. So the input side we generally do the forward biasing because we want to give. Now, can you tell me collector should be reverse bias or forward bias? Difficult, I'll tell you. So as of now, remember, it must be reverse biased. So how to make the output reverse bias? Any guess? By connecting this as
Higher potential.
higher potential. So this we can call, what should the name here?
DC.
VCC. Okay. And in the reverse bias, we don't represent the barrier potential, right? We represent the barrier potential only in which case? Forward bias, isn't it? In reverse bias, do we represent the barrier potential? No. Hello. In the reverse bias,
we
do
do.
we represent any potential?
No.
No. Barrier is only when you try to break it, right? Barrier is opposition. Okay, anyway, what is the potential here? C is at, this is, you can say V, which one is bigger? This is VB, this is VBC. This is reverse potential. No, this is opposite only. This rise, fall. The naming should be okay. VBE, VBC. All right, this is VBC, correct. So now I'll come to this. Why we do the reverse biasing? So here this is reverse biasing. Here it is forward biasing. So before we do the biasing, I'll tell you why we do all this biasing. Okay. There is a reason. This is a technical reason. There are three types of operation in transistor. Okay. Or there is a three region of operation in case of transistor. So we'll see all the three region one by one. So let's put this as a mode of operation and biasing. So for particular operation, we have to do a particular biasing. This is what we have to learn actually. So there are three reasons for biasing. And we have input side and we have output side. And depending on which region you want to operate the transistor, you have to do a certain biasing. So if you want to, let's say, operate the transistor in a region called cutoff. Cutoff is also called the off state. So if you want that your transistor should not work at all, don't give current. How to stop giving current? How to stop giving current? Make the input reverse bias. Emitter will never give. Understood? So what you are supposed to do, make the input itself off. This entire circuit will be off. It will not connect anything. So for cutoff, the rule is simple. The input must be reverse bias. I mean, the p junction should not work. That's the whole idea is when you draw a p junction and if you draw the input characteristic, if you don't want any current, then make it a reverse bias, because in reverse bias we don't have any current except the saturation. But that is negligible, isn't it?
Yeah.
And the output must be always reverse bias. This is called off state. Okay, what we call off state. The other is called saturation. To operate the transistor in the saturation region, which is also called the on state, to operate in the saturation, what you have to do? Make the input and output both forward bias. Both. In these two cases, we say that transistor will act as switch. Wait for some time. I know this is not making sense to you. And the last is called active region. And this is the region which we are mostly interested in. In active region, this is called the amplifier. So you amplify the either input voltage or input current. And for this, we have to do this practice to operate the transistor in the active region. The input must be forward bias so that the current is let go, and the output must be a reverse bias. Okay, and in this case, we say that transistor act as amplifier. So in this region, transistor act as amplifier. So we'll see one by one, no need to worry. So in most of the configuration, when we draw the diagram, we draw for the active region. But let's see why we are doing this, forward and reverse. Why we are doing this? Let's see one by one. So for this, I need to draw a really big diagram. Emitter, a collector, but I'll draw a big collector. I'm sorry, base. And we have collector. N, P, N. Okay. And as I said, to operate the transistor, the input side must be which biasing? To activate the
Forward.
transistor, we must do the forward biasing. And for forward biasing, N must be negatively charged.
Yeah.
And this must be positively charged, right? So this is what we did. This is the first step. All right. So now what will happen? Now the current, which current will flow? The majority will flow, isn't it?
Yes.
So what is the majority here? Electrons.
Electrons.
E, 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 E. So before that, we have to also do one thing which I have missed. Depletion region. In the forward biasing, the depletion region should be very thin.
Yes.
Correct. But because we are going to make the output reverse bias, the depletion will be thicker. Now tell me, is thicker good or bad? Guess. is thick good or bad? Okay, we need thin so that the electron can cross this layer easily. And what you want? You want these electron to enter which region? Collector. So as the thickness of the depletion will increase, it will be easier for the collector to receive these electrons, isn't it? It is like the
Yeah, the
collector
field
is
strength will increase, no?
the collector will try to reach out to these electrons.
Understood. Yeah.
And to reach out to these electrons, it must be thicker, isn't it? Understood what I'm saying? So for increasing the thickness, see what we want is that this coming electron should easily get into this part. And because we know this is the PN junction, so this side is negatively charged. This is
Positive.
positively charged. So certainly we do have electric field this way. Correct?
Yes.
So the moment this electron will enter, it will be pulled by the field easily on the other side. Isn't it? So what we
Yeah.
want is, we see the collector will try to receive as much as possible. But the problem is, to receive as much as possible, it has to extend its boundary. And that can only be achieved if the output is which bias? Reverse or forward?
Reverse.
So I hope this is logical. Do you all realize this? This is logical. And also, we should make sure that the depletion, the entire base region is as thin as possible, isn't it? Hello, tell me. What we want? We want the depletion, the base region, this entire gap should be as small as possible. Because as you make the narrow, the entire base itself, it will be easier for electron to jump from this side to that side, the collector side.
Yeah.
And so now you know why we have the size. Do you realize the size case?
Yes, sir.
So we take the emitter like somewhat bigger size, but not the biggest. Collector is biggest one. And base we keep as thin as possible. So now only the base is kept in a few micrometer range. And the whole idea is, the entire diagram which I have drawn on the entire this blackboard screen is only few hundred micrometers. That's it. So these are like chip level designing, and you can see clearly the purpose of this collector is. But anyway, however reverse bias you may increase, you cannot go to the breakdown region, isn't it? If you remember, we are not supposed to cross the breakdown region, correct? Hello. See,
Yes,
reverse bias having the danger of breakdown. So in the greed of receiving more and more electron, you may try to make the reverse biasing really large, because people are greedy, but God is smart. If you try to be smart, it will break the entire device, burn the device. So once it will go in the breakdown region, it is of no use. So it's a danger. In transistor, when you buy a transistor or any electronic device, they come with complete specification. And the specification is that you should not use more than this reverse bias. It's dangerous. Okay. So people are greedy. And just for the sake of current gain, they will make the reverse biasing as much as possible, and then you know what will happen. I don't like it. So the motion of the current majority will go here. It will reach here for sure. And because as I've said, this is a very thin part, but something will go here, right? So some electron will go here. Of course, the majority of the electron will go here, no doubt about it. Correct?
Yes.
But some will go this way also. As per the conventional direction of current, can we say this current is IE? Because current is opposite of electron, right?
Hmm.
So because electrons are going this way, and always remember the giver is the donor is only emitter. Okay, so base and other are a receiver of majority carrier. I'm not saying current, the receiver of majority carrier. So can we say current is flowing this way? IC. Current is opposite of the flow of electron, isn't it? And you can see the base electron is going down. So can we say current is here like this? Hello guys, can we write? Hello.
Yes.
Can we draw like this?
Yeah.
Tell me. So generally we don't show internally, we show near the terminal. So we have terminal, and therefore this IB is correct. We show it IC here, and we show IE. Yeah. So if I take the entire device as one single dot, if you think the entire device is a single dot, how much is incoming current? Kirchhoff's current law. So what should be the relation between IC, IB, and IE?
IE is IC plus IB.
Always true. This is, see, I have derived for this device, but no matter which device you use, whether it's NPN or PNP, as long as it is transistor with emitter, base, and collector as terminal, your answer is going to be IE equals to IC plus IB. And also by common sense, you can say something. IB is going to be very, very small compared to IC. And IC will be almost equals to, but on a lesser side, I. So
Yeah.
majority current is IC, of course. I mean, IB is contributing in microampere, IC in milliampere. That's the ratio generally. So the first question that they will ask you, the relation between these three, IE, IC, and IB. And I think this relation is quite obvious. If I change this diagram to PNP, then I have to just reverse the direction of current, isn't it? Hello.
Yes.
So if you draw the transistor circuit diagram for this this circuit in which we have common base, this is basically common base configuration, right? CBC, common base configuration. So you can draw this quickly. So if you want to draw in a circuit diagram, not in this actual diode, and let me draw for the NPN always. NPN is the most, you can say, universally used device type. Okay. Collector, emitter, base, arrow, and now it's, I think it's very easy to understand. This is your I, this is your IC, and this is your IB. Correct? This is the diagram.
Yes.
So from there to here, I think this won't be a difficult task for you to draw the diagram. All right. So what is input here? What is output here? For common base configuration, we define alpha DC. This is called the DC current gain. So you can think gain as a efficiency or gain, or in general, when you learn this term gain in semiconductor chapter, it is always the output value upon. So here, what is we are gaining? The current. So how to understand how much we have gained? So we can say output current upon input current. That's it. So tell me guys, what is output here? What is output here? IC.
Collector.
And what
Yep.
we are giving the input?
IE.
I. That's it. So this is called the DC current gain. Okay. For common base. So generally for common base configuration, we define the DC current gain. That's it. This is called DC current gain. But we also know something. You know what we know?
Sir,
Hmm.
will we not add an IB term to both of those?
Yeah, we can. We are going to do that only. So we can also write this IDC equals to what is IC we can write as? So if it is common emitter, some generally we write like this. So we can write IC and IE we can write as IB plus IC. Isn't it?
Yes.
So you can write it this way. IB plus IC upon IC equals to how much? 1 by alpha. Correct?
Yes.
So IB upon IC plus 1 equals to 1 by alpha. So what is IB by IC? 1 minus alpha by alpha. Correct? Hello, hello, hello. I hope this is clear. Hello. So what will be the IB,
Sir.
IC upon IB? Yeah.
Sir, I texted you a
Yeah,
message.
Just a moment. Just a minute. Yeah, no problem. Just take rest. Okay. You can listen to this recording. Okay.
Okay, sir. Yes, sir.
Yeah, good night. Take care.
Good night, sir. Thank you, sir.
So the IC upon IB, what we can write? Alpha by 1 minus alpha. Correct? And what is IC here? Output. IC is also output. But this is called the common emitter configuration current gain. So we have a symbol for this, which is called beta DC. What is beta DC? Current gain for common emitter. So we call this entire term as beta. So what is beta DC, guys? Alpha by 1 minus alpha is called beta DC. And this is called common emitter. If I want to write it, let me write fully. Common emitter current gain. Okay. So these are two notation, and in fact, this is the question you will see in the examination. A direct question based on this two formula. So alpha is IC by I, and it is close to how much? 96.5%. I mean, you can say the alpha range is generally 0.96 to 0.995. So alpha is close to 1 value because IC is almost equal to IE, but slightly less. Okay. What is beta? It is IC by IB, and IB is very small compared to IC. So this answer is roughly in the range of 200 to 300. This is a typical range of the beta. When you use a symbol like this, we call DC gain, and sometimes we don't write the subscript DC. But when you solve the question in which we have a biasing voltage along with some small signal, you attach something like a sinusoidal wave, along with that. It's called a small signal analysis, in which you vary the value of current of input by a very small value, not much large. So whenever we have the difference of value in both sides, it is called AC value. So we have AC current gain. AC current gain for common base configuration. And how we write? Alpha AC. When I write AC, it is the difference value. So how to write delta IC upon delta IE? This is how we write. So how to understand that, sir? We have to use this. In the example, they will give you the IC plus minus value. So from there, calculate the change, the maximum difference, and then divided by the difference of IE, you will get the alpha AC. Then we have AC current gain for common emitter configuration, and the answer will be beta AC equals to delta IC by delta IB. This is how we write. These are very typical ways of writing. AC means difference, change, because AC signal means a variation is there, and DC will have constant value. So whenever there is a variation, we find the change in the input value and corresponding change in the output value. We take the ratio, we call AC gain. When we have constant circuit, constant source circuit, we talk about the DC gain. So these are some typical way of writing the answer. I hope this is not difficult. The gain is clear? Hello.
Sir.
Yeah.
When you started your transistor, you had said that when the common terminal will act as both input and output. So here, suppose for the common base configuration, won't we have to add an IB term at the top and the bottom for the alpha DC, suppose? So IC plus IB upon IE plus IB.
In this case, this common base.
Yeah, you said that the common terminal will be both input and output.
Yeah, so we never see the biasing of IB. We see the biasing of the terminal left after the common term. So this is, you can ground it also, right?
Yeah.
Just to avoid any controversy. But generally, when we talk about the biasing of the input and output, we only look for this and this. We never see the common term.
Oh, okay.
Common is not seen. It is only the top two is seen. So that's a good question. I expect someone should have asked this question. Very good. Okay. So this is the common base configuration. How we write circuit? How we write the equation? Okay, let me show you the common emitter and common base both one by one, and I'll show you how to draw the circuit. So I'll do first common emitter configuration. Common, just see first emitter configuration, CEC, and how to draw. So you have to make now emitter common. Okay, and to make emitter common, it should look like this: base, emitter, and we are done. Now you're not supposed to remember all this diagram. I mean, see, the thing is, in examination they will give you diagram. You should know how to solve it or how to write it. Okay. This is base. If I put the arrow, emitter, collector. So you have to do the biasing first. While doing the biasing, there are many choices. See, the first thing is you must make the, because this is NPN. Let's say I'm doing the NPN transistor. So in the NPN, the input must be forward bias. So how to make it forward? The P must go with high voltage. Correct?
Yes.
So this we can add as VBB. I mean, that's how we represent, isn't it? Now, beyond this, you can do many manipulation. You can always play with the idea. Okay. You can always play with the idea. What is the idea? So you can put some resistance here. If you want, you can put resistance here. And you can call this resistance as RB. It's up to you to name it. And on the other side, you can again put the resistance. And you can name it RC. And generally in the output side, we do put the RC. This is what we do generally. And to make it reverse bias, we have to make this like this. I hope so. You can understand this part.
Yeah.
And this name is going to be VCC. And some potential we should know that this is called VCE. If you go this way from here to here. Just a minute. This is called VCE. And similarly, you can, okay, you know which one is at high potential? This is high. Just a moment. This is high, this is low. Okay. So the barrier potential is going to be like this, no? This high and this low. I hope you remember this barrier potential. Barrier potential will always oppose the biasing. Just to remember the fact. Correct?
Yes.
And how we name it? We can say VBE, base to emitter. This is called base to emitter. The biasing in this barrier potential. Okay. Now, how we solve question? Generally, how we solve question? So we know that terminal current is known to us. See, whatever be the configuration given to you, this current will go enter the terminal. Yes or no? Like this. This will enter, isn't it? And this IV will enter like this. If both are entering, then IE will exit.
Exit.
So this configuration given. Now, if I draw some resistance in the emitter junction also, it will have some equation only. But technically, this is what you need to know. To solve any question, I mean, you're not supposed to be genius. You can solve by simple KVL. Okay. So the question is how to write the KVL. How to write KVL. What you can do. So we have two circuits. We have input circuit and the output circuit. We have two circuits. And the first question is KVL, KCL. So what KCL will give us here? If you apply KCL for the entire circuit as a node, if I choose the entire transistor as single object, then KCL will give me the same answer. I equals to IU plus IC. It is clear? Hello.
Yes.
Hello guys. Now the next part. What is the beta DC? The current gain for this configuration. See, for common base we call alpha, for common emitter we call beta, for common collector we call gamma. Although gamma is not asked, but Alpha, beta, gamma is as per the common base, common collector, common emitter. Sorry, common emitter, common collector. Okay. So generally we stop at beta only. You can also define gamma, but okay, it is not defined generally. So for common emitter configuration, the beta DC will be how much? Output upon input. What is the output current? You can see the output current is how much? IC. See, output is here, no? Collector is the output, isn't it? And base is the input. Hello.
So collector is giving the current into the transistor, right? And
No.
current we are taking out of the transistor is IE.
No, don't think this way. The majority charge carrier is given by the emitter.
Okay.
Current flow is opposite of the charge flow, right? In this case.
Yeah.
So collector only receives. So
Okay.
collector is receiving here. And what is it receiving? It is receiving electron here.
Okay.
This is NPN. So the current IC is not given. I mean, the collector is not giving to anyone. It is the emitter which is giving, by virtue which IC and IB is there. Understood?
Oh, okay.
So the IC is what? IC is the output value. Okay. And what is IB?
Input.
Input. Now the thing is, when we say gain means output upon input. So what is output here? IC. What is input here?
IB.
IB. A presence of IB is necessary. Why? Why the presence of IB is necessary? Because when you look in the diagram, IB is the manifestation of the fact that circuit has achieved the forward bias. It means you have crossed the barrier potential, isn't it? See, if VBB is exceeding the VBE, our input is forward bias. Yes or no? Hello.
Yes.
See, if VBB, which is the biasing battery voltage, exceeds the barrier potential VBE, then our input is forward bias. Okay. Hello.
Yes, sir. Yes, sir.
And if it is forward bias, then it is confirmed that IB will be there in the input current side. So when you have the common emitter configuration, we don't look at IE, rather we look at IB. And if IB is present, then IC will have hope. If input, you can say, if the input side of the circuit is active, then only IC will receive anything, isn't it? So IC cannot actually, come into picture if input circuit is not forward bias. Do you realize this fact, what I'm saying? See, if you look at the PN junction from the output side, it is reverse bias, yes or no?
Yes, sir.
So reverse bias cannot have the majority current carrier, isn't it? Reverse bias means what? This PN junction is not creating current, rather it is receiving current. Okay, I think you are still not clear. See, look at this diagram. Is collector producing current? Tell me yes or no. Or it is only receiving the majority carrier? Tell me. That's what was happening here.
So it's receiving the majority carrier.
So a reverse bias PN junction cannot have the current, na? It can have only reverse saturation current, yes or no?
Yeah.
So reverse saturation current is almost nothing, it's almost zero, isn't it?
Yes.
So here, just because you see IC, but is IC its own manufacturing, or it is just a beneficiary of someone else giving to it?
No, it's not due to its own.
So it is a direct beneficiary of emitter, no?
Yeah.
It is a beneficiary of emitter. So you can say it is a beneficiary of forward biased input circuit. Yes or no?
Yes.
It is the beneficiary of forward bias input circuit. Does it make sense? So IC will never come into picture as long as the input is which bias? Hello, hello, hello. Oh my God. Okay, the gain is clear. The DC gain is clear. So alpha beta relation I have already derived, so I will not derive it further. Alpha is what? Tell me guys, for alpha, what we should think about? Common base configuration. CVC alpha, CEC, beta. Okay.
Yes.
Hello, hello. CBC alpha and CEC beta. Okay. This part is clear.
Yes.
Let's write KVL in loop 1. See how simple is this? How to write KVL in the loop 1? Let's walk. You begin from here. IBRB minus IBRB minus VBE plus VBB equals to 0. Is this clear, guys? Tell me. Hello, hello, hello.
Yes, sir.
So the answer for the okay, whatever you want, you can find IB equals to, you can get the answer from here. IB is VBB, the biasing minus forward bias barrier potential upon resistance. Simple answer. So they will generally give you the answer. You can find IB. And how questions are made actually? You have to find the IB from this logic. Then they will give you beta. Once you have the IB and beta, you can find every other value. Correct? So if beta is given to you, if you know the current gain, and if you can calculate the IB, can you get the other variables like IC and IE? Tell me guys, yes or no?
Yes, sir.
So I can say that the IE will be how much? IB plus IC, which is beta IB again. So 1 plus beta into IB, and IB I got from here. I can get the other answer, IE. So these kind of question will come. I'll show you some question, don't worry. Okay, first let's try to learn how to write the this. What we call? Write this. The KVL. In the loop 2, how to write KVL? Just click the picture. I will go to the next page. In the loop 2, how to get the?
ICRC.
Yeah.
ICRC plus VCC.
So VCC minus ICRC. If I start from here.
Yeah,
Correct?
plus VCC plus ICRC. Exactly.
Then which one is at high potential? Then we have to write VCE minus, no?
Yeah, minus.
Plus. So we can say minus VC equals to 0.
Yes.
So VCE is called VCC minus ICRC. This is very important relation. And make it, highlight it in your notes if you're writing well. Now, why this is very, very crucial, I'll tell you. So you got the answer, VC equals to VCC minus ICRC. Okay. Now tell me, once you switch on the input circuit, IC will come automatically, isn't it?
Yes, sir.
And if IC will come, then VC will decrease.
Yes.
So as the IB will grow, VCE will
Decrease.
and that's important. So there must be some value of IC which can make VCE 0. Isn't it? Quite possible. Because there is a difference, so eventually it may become 0, no? Quite possible it may become 0, yes or no?
Could be, yeah.
No, why not? If VCC equals to minus ICRC, then it is 0. So in that case, this will become short circuit, isn't it?
Yes.
You know what is short circuit? I mean, the base will not matter. Everything will start from the emitter, will go to collector.
Yeah.
That's called short circuiting. This condition is called saturation state. When VC becomes 0, we say the circuit has gone to saturation state. And this is generally achieved when it is also a forward bias. When it is also forward bias, things will change in that fashion. Okay, anyway, so we'll come to that later on. But this is the diagram. I'll give you some question to solve, to practice. But before that, we need to learn how to draw the input and output characteristic of common emitter configuration. I think I have missed the graph for the common base. So, okay, let me do both one by one. Quickly, I'll do it. Characteristic graph for input and output for common base configuration. How to do graph and why we do graph? Let's try to understand. The input graph is for PN junction in the reverse biasing, isn't it? Hello.
Yeah. Input is IC, so PN, yeah, reverse bias.
So in the common base configuration, if base is common, what was the input current?
IE.
IE, very good. And this is always in milliampere. Why milliampere? Because in the forward bias, we have milliampere.
Forward bias.
How to write here? What to write here? The bias voltage. Should we write VEE or should we write a VEB? So we don't write, okay, I will tell you. We don't, yeah, we generally don't write VE. The reason is I may put some resistor also, no?
Oh, yes.
So will you get a VB, VEE? The answer is no, you won't get a VE.
No.
So if I make a circuit, a generalized circuit in which I put a lot of resistor and something. So let me show you here quickly. You will understand, don't worry. I hope you have understood why I'm saying this. Now, can we say VE is what it will receive across the junction?
No.
So generally, the barrier potential is inside, but we know that this voltage V,
EB.
this voltage should be the input function. Like we should know what is the potential across the E versus B, isn't it?
Yes.
We should know this. I'm not saying this is barrier potential, but what is this value? The applied value. If the applied value is more than barrier, it will conduct.
Yes.
If it is less than barrier, it will not conduct. Okay. And the input characteristic will just follow the a graph like this. This is a simple graph. It is
But how do we vary the EV-EB? Like
Pardon?
that is characteristic for whatever the PN diode we use.
We can use variable. No? We can use variable. This is variable.
No, VEB. That
So,
is the constant for breakdown voltage is constant for a certain.
A breakdown voltage. Okay. The thing is, when I'm writing here a VEB, I'm not taking the VEB as the breakdown. I'm taking VEB is the net potential across these two terminals, which should be more than barrier.
Okay. Sorry, not breakdown.
Because when VEB exceeds the barrier, which is not shown here actually, then the current will establish, right?
Okay. Understood.
I mean, there are so many symbolic confusion. I know it's the way NCERT is given things. It has been really complex. Okay. This is barrier. So definitely the VEB must exceed the barrier. Okay.
Yes.
On the collector side, we can again have some resistor RC. And this must be reverse bias. And generally we obtain the output across the load resistance which you connect. So this is how we get the output if required. But anyway, the bias voltage, let's call VCB. When we draw the input, we make sure that the output is not changing. It means we try to make the output configuration constant when you draw the input characteristic. That's the rule. So when you draw the graph, what we must keep constant there? VCB, the output bias voltage. The output bias voltage, we have to keep constant when you plot the input.
Okay.
Because output bias voltage can affect. And it will certainly affect. If the output voltage, you make it positive. I mean, if you make it, for bias, will you get the same emitter current? The answer is no.
No.
If output is, let's say, 0 bias, will you get the same answer for IE? No. If output is reverse bias, will you get the same answer? It means if output is biased to certain value, then we'll get different values of current, isn't it?
Yeah.
So biasing will decide. I mean, of course, the input characteristic will not be constant. Rather, it will vary as per the output value,
bias.
the VCB. Now, there is a question, common question. As VCB will increase, what will happen to the emitter current? Okay, this is okay. This is I have mentioned. This is the effective value cross terminal E and B, not the barrier potential as used before while applying the KVL. So on the last page, I applied the KVL. Now, there was a question here. What will be the effect when you draw this input graph? We have to make sure that the output, biasing is constant. You draw it for one particular VCB. So the question is, as the reverse value, let's say this is minus value, minus VCB. It's simply reverse value. So as this value will grow in value, as you increase the VCB, as the reverse bias voltage is increased across the terminal, what do you think will be the effect on the I? Will it increase or decrease?
It will increase. As the reverse biasing increases, the current should increase.
Yeah, it is always increasing.
Because
That's
of that
correct.
capturing
Yeah.
value that you showed.
So if you draw graph like this, let me make it slightly bigger. If I make this as VCB1, if I call this as VCB2, if I call VCB3, so currently which VCB is maximum? Which VCB is maximum here?
VCB1
is more than
VCB2, more than VCB3.
So this is also a question which was asked in the JEE-Mains actually, I think, and you should know this answer. Okay. Now the question is how to draw the output characteristic graph. That's very interesting. So I'll mention this note. To draw the input characteristic graph, output bias voltage must be kept constant. What about the other way around? To draw the output characteristic graph, input current. Now here is very different. When you draw the output graph, the input current, because input current is very prominent, right? See, output is going to get everything because of current only. So output current is not by virtue of voltage. If you remember, it is by virtue of current coming from the input side. Yes or no?
Yes.
Output current depends on the incoming current of the majority carriers due to the input side.
Yeah.
So voltage is not deciding, na? What is deciding? The current value, correct? So when you draw the output characteristic graph, input current, which is IB in this case, what is the value? In this case, I must be constant, isn't it?
Yes.
Hello.
Yes, sir.
See, IC will only see one IC will be because of one I. So as you change the I, IC will change, isn't it?
Yeah.
Okay. So how we plot the graph of the output characteristic here? Okay, I'll do it in a separate page. Do we have a space here? No. Okay. I know it is getting now overwhelming with the fact, isn't it?
Yes, sir.
So now many are losing patience now. It's too much now. Okay. So what is the output current here? IC. And what is the voltage part output? VCB. Correct? And then you plot for various IE. Okay, so for one IE, there is one graph, and then so as the VCB, I mean, will increase in value. I think this should be in reverse bias. Actually, these are the negative values. Minus 1 of 10 minus 2, 4, 6, 8, 10. Because VCB is always the reverse bias, right? Correct?
Yes.
Okay. So the graph will how it will look like. If you plot the graph, you have to plot the graph for one particular value of IE. Okay, so let's say you choose some IE, and graph looks really different here. So before I draw the graph, I'll draw something like this, a line, and then I draw the graph. So the graph will go like this. If IE is almost 0, the IC cannot be more than that, right? It is also going to be almost 0, isn't it? So if you release less value of current, IC cannot get more than that, isn't it?
Yeah.
But also to receive that value, VCB must grow in value from the 0 to some value of negative value, some negative, biasing voltage, right? If you release a large value of IE, then also IC will become eventually constant, but for some other I2. If you grow IE further, the same graph you can obtain like this. IE3, and then
So what is the red vertical line for?
yeah, I'll tell you. The reason beyond this is called the saturation region. You know why it is called saturation? Because a reverse bias is the case of active region. If you are close to 0, it means if you are now close to 0 means what? If you go beyond this, you will get a forward bias.
Forward bias. Yeah.
And once you get into the forward bias condition, you become in saturation region. Because in saturation region, the input and the output both are forward bias. Okay. So it is like, I mean, of course, I can show -5, then I can show some positive value also. So you will go into the forward bias region. So you enter the saturation region. Okay.
Okay.
And if I is nothing, below this line is the, so basically this below this line is called the cutoff region. I mean, it's difficult to show. This is cutoff. Cutoff means the input itself is a reverse bias. I mean, there is no I. If you make I itself 0. If there is some I, there will be some IC.
Yeah.
If I is not there, if I draw I something like this, then there is no IC, no? Okay. So below the region is called, it's always below the axis called cutoff region. This range is called saturation region. And everything right of this is called active region. And it's having some slope. This is not exact graph. This is, so if you draw a graph like this value is how much? Delta I, correct? Sorry, delta IC, my bad. And this is how much? Delta VCB. You know what this slope is called? This is called the output resistance, AC resistance. So our AC is defined as delta VCB upon
delta IC.
that's it. So this is called dynamic resistance. You know why dynamic? Because these are not constant. As the slope will change, the resistance will change, isn't it? And as delta IC tends to 0, RAC tends to infinity. I mean, very large actually. So the rule is simple. The dynamic resistance, to calculate, we have to find the slope and take the inverse of it. And dynamic resistance is always determined from the graph using the actual slope or finding the difference. Okay, this is how we find the dynamic resistance. If it is a perfectly straight line, then the resistance becomes static in nature.
Infinite.
And it becomes finite in nature. So in semiconductor, the world of semiconductor is very strange. The resistance is always dynamic. Okay. So this is IE1, and therefore, so what is the ratio of I1? Which one is bigger? As you go up, I will increase, correct?
Yeah.
That is obvious. Okay. So this is how to draw the characteristic graph of the common emitter configuration. Let's do the same. So are you able to digest, guys, or is it getting too much difficult?
Okay, sir.
So it's enough that I'll have to watch the recording at least once.
Yeah, if you want to really grab it, just watch it once. I mean, there are many facts and figures. Like there is a new circuit in which you have to interpret things differently.
Too
So I
many
know,
terms.
yeah, there are too many terms, and suddenly the life is hell. But we are very close. I'll try to finish as much as possible today. Then only thing left will be the logic at which we can finish in 15 minutes in next lecture. So in some of the lecture, I'll capture that. But I'll finish this today. I'll just give you formula. Just, you can kind of mug up the formula and solve it. Okay, what is the input characteristic graph for common emitter configuration? Okay, slowly. When the configuration is common emitter, tell me what is the input here? Input current is
IB.
And so the input voltage will be
VBE.
that's it. So plot the graph between IB versus VBE. Is it okay? Hello,
Yes.
guys. Okay. And if it is okay, then because it's again a regular PN junction with forward biasing, so you won't get some surprise here. You'll get the similar graph. Okay. So what will be the graph? A regular graph which we draw. So only when you exceed the barrier potential, graph will come into picture. But when you plot the graph, what we keep constant?
IC.
IC is never into picture without IB. When you draw the input graph, we keep the output biasing constant.
Okay, yeah. Bias.
When we plot the output graph, we keep the input current constant.
Yeah.
Difficult. it is like you need to understand the dependency actually. And once you understand the dependency, then probably you can remember. So while drawing the input graph, what should be constant in the output side?
Bias.
Bias, voltage. But while drawing the output graph, the output means, see, characteristic means IV graph, basically, current versus voltage graph. So when you're plotting the outside, what we should keep constant here? The inside?
Yeah.
What?
Outside is output, right? You're
Outside
plotting
means
the output. Output is depending on the input current. So input current.
So we have to keep one value of input current. Understood? Kind of.
Yes. Yes.
Okay. I'll just show you. I mean, with some practice, you will see there is a pattern. Just it takes some time to digest the pattern. Not difficult, but yeah, too much informative. I would say after reading twice, make a notes and remember the fact. Don't try to understand much. I mean, if you remember the fact also, that's good enough. So the IB is always in microampere, as I said. And I have to keep the VCE constant, right? This is constant. I hope you understand this.
Yes.
Okay, guys, tell me which one is bigger.
Three greater than, two greater than.
Very good. Because we know that if the biasing will increase, IB will lose the marks. Because the collector will try to proceed to collect as much as possible, right? So base will get nothing.
Yeah.
See, this is the basic circuit which you have to remember. This is the only fact. This is the only entire transistor is here only. Whatever I do doesn't matter. If you can remember this diagram, you can answer. So common sense, if the depletion will grow, if this depletion will grow, the base will lose the current, no?
Yeah.
As I will grow the value, then I can collect more, no? The chance of collecting will increase, isn't it? So base will get lesser and lesser. Hello.
Yes.
Do you all realize this? So it's a very interesting, I mean, in this case, the VC will grow and IB will decrease. So I can clearly see VC is more than VCE2 is more than. So note, with increase of output reverse bias voltage, IB will decrease because it will be easier for majority charge carrier to enter collector. I hope this will help you. Okay.
Yes.
And again, you can define the DC dynamic resistance. So this is delta IB, delta VB. So input dynamic resistance will be how much? Input dynamic
V upon delta I.
So R dynamic or RAC, delta VBE upon delta IB. So whenever you're solving question in examination, plot the graph, just try to understand what is input, what is output, and hopefully you can get the answer. Okay. So this is Ri in. I can hope that you can remember. Shall I hope? Okay.
Right.
And see, after transistor, I know no one learns this chapter. So mostly I have, that's why a diode is something till everyone is comfortable. And I have seen that, okay, after diode, okay, you need really to have a lot of patience to understand. But if you understand, I can guarantee that you are going to get marks in this chapter for sure. No matter what. So now it's like 50-50 luck. If diode will come, I think you will be comfortable.
Yeah.
If transistor will come, I don't know.
I'm sure yet.
No, but still, if you have, if you have heard all this thing, hopefully by looking at the option, you can guess which one is bad option. Most probably. So
you
will get some idea. I mean, that is for sure. It is not like you won't get any idea. Idea will come. But anyway, I would say, okay, just try to understand this lecture once again. It's not difficult. It takes some time to settle down. That's it.
So all of what we have studied till now is just for NPN.
NPN is what we have to study in our syllabus. That's it. PNP is not there.
Okay.
In fact, in BTech also we have only NPN. PNP is generally avoided.
Oh, okay.
It is like you have to proceed by either assuming NPN or PNP. So most of the professor, most of the books written, they have been comfortable with NPN since the beginning only.
Okay.
Because the only difference is the flow direction, nothing else, right?
Yeah.
So output characteristic graph. If you want to go, you can go. I'll finish it and you can watch recording. I'm also okay teaching alone. This topic is now I want to finish today itself. Rest is just watch it. Because only topic I'm going to leave is the logic gate. And I'm very close to finish it. Okay, output characteristic graph of common emitter configuration. So again, so who is going to stay with me today? All right, okay, I got one.
For me.
Great. So this is your VBE. This is your VCE. And in output, we plot the which current? IC. And which voltage we take? The biasing voltage, right?
Yes.
Slowly we'll get the idea what I'm doing. That's why this is a topic which no one wants to teach. Okay. Sometimes it gets really boring. But it is very useful if you go for the electronics or computer science. Let me tell you, even in BTech also no one is going to explain. I mean, you have to read the book, you will understand from book. Books are really good. I mean, they are very good book. By reading which you can understand.
If nothing else, we'll still have these archived lectures.
No, this lecture will be there, so you can always watch. I'm going to put on the YouTube, so anyway you can watch. So the first semester you can easily pass with these lectures. At least the 70% of syllabus of first semester. This is basically called BJT. Bipolar junction transistor. But in BTech we'll also study FET. Unipolar It is actually called field effect transistor. So FET is, and of course we study more of the FET. FET means the charge carrier is only one, either hole or the electron. But in BJT we have both our charge carriers, electron and hole at the same time. So in BJT,
majority, minority, or just
no. Actual current. In BJT, the current itself is IE plus IH. I have written somewhere. No?
yeah.
I mean, I don't know where I have written. Yeah. Understood.
Yes.
So all the transistor when you create, in which both are carriers. So in the valence band, generally holes are the current carrier. In conduction band, it is electron. So the net current is sum of the two actually. Okay. Okay, how you are going to draw this diagram? Again, the same fashion. Draw a line here. So below this line will be cut off.
Cut off. So
This is cut off. This is negative axis. I mean, because negative axis means you know. And then because it's common emitter, so input current is what? IB. So we plot a graph for one IB. So this is almost 0 IB. So below this is IB 0. You're into the cutoff region. Then you as you increase the IB, or you can say as IB will come into picture, which means as the input gets forward bias, the IC will come into picture, right?
yeah.
Okay. So, okay, similar to this region is
Saturation. Right.
saturation, because as you go towards the 0 voltage, you enter the kind
Forward
of
bias.
forward biasing. So this becomes the saturation. Okay, cutoff is below, and this is the active region. And you can draw a slope here. Delta IC. What is our output? Dynamic resistance. So I think this is not difficult graph to remember, right? Is it difficult?
Not really.
Not really. I think, do you have energy to continue, or should I leave and next lecture? Nothing is left. I mean, hardly 20 minutes is left.
No problem.
No problems.
Are you sure?
Yeah, sir, you can continue.
Yes, sir.
Okay, let me continue. Anyway, I have to solve question also, no? Then only this will matter. So now we have common emitter as an amplifier. So the idea of amplification is like this. Of course, every circuit we can create with two types of input values, constant input values, like if you connect DC battery everywhere. In such case, what you gain is called the DC current gain and whatever. The other idea is we can use a transistor in which, apart from the biasing which you connect, we do connect some input signal. In a way, you have some sinusoidal source which you connect in series with the biasing voltage. So we call this as a small signal analysis. Okay. So let me show you how a circuit looks like for the amplification purpose in communication channel generally, and how we solve it. So you need to know a lot of things here today. Let me show you as per NCERT. Again, you're not supposed to mug up any of these, but of course, there are certain formula which I will request you to remember. Okay. So we
Yes.
start. So for amplification, it must work in which region?
Active region.
Active region, correct. So for amplification, this must operate in active region. All right. So let me do the diagram. So generally we connect a resistor to get the output. Okay. And okay, we also need to connect a bias voltage. We connect the bias voltage here only. It's the same circuit, but I have just reduced like this. And this is NPN. So this must be reverse bias. And this is VCC. And we assume this to be variable because of the input signal. Then what we do next is we connect a capacitor, and across the capacitor we derive the actual output. You know why? Okay, you must be wondering why. A capacitor can only allow the high frequency signal, right?
Yeah.
Because, okay, through capacitor DC current flow, if you remember.
No, once it starts, the current flow stops.
Yeah, so it is very quick process, isn't it?
Yeah.
So capacitor generally do not allow the low frequency, or you can say DC current. it only allows the AC value. Okay. And when you have this combination of DC and AC element in a circuit, capacitor will block the DC element and will let you have the AC element, and therefore you get a signal as a output. Let me do the input also, then you can understand better. Okay.
So what do you mean by signal?
Actual communication signal, any input signal, like the voice signal, whatever.
Okay.
Yeah. So again, you can draw a similar diagram. This is RB, and you have a forward biasing here. This is VB, and this arrow means it's a variable. Why it is variable? I will tell you. It is variable because this is going to be superimposed with a capacitor, and this capacitor is connected with the sinusoidal source actually. This is the new diagram. So what happens? The voltage which you will receive, or you can say the current which you will receive, there are two types of current you will receive. So this IB will be the IB due to the biasing which we have been receiving, plus minus some extra, right? Because of this AC. Because through the AC, through the capacitor, will also send some current. And this current is anyway coming. So you can think this current as the delta IB. And this is the, because IB is very small, delta IB is going to be even smaller only. But this is how we think. Okay. Now we want to, only amplify the AC part, not the DC part. Because the amplification means, see, you get some energy, you increase that energy. So isn't it the violation of conservation of energy?
Yeah, kind of.
But the answer is no, it's not violation, because we are not increasing the net energy. We are increasing the input signal energy at the expense of loss of DC energy. So generally, and of course, we have the current, a power supply. So let's say you receive some information or signal through a transmitter. Transmitter, travels and comes to the device called booster. So in a long distance communication, if the energy will propagate for longer distance through the channel, it will get attenuate or weaker. So what we do is we have intermediate device which receives those signal and further do the amplification of that signal at the expense of course, loss of the DC energy. But that's very insignificant, because these signals are low amplitude, high frequency signal. Low amplitude and
high frequency.
High frequency. Now the beauty of high frequency is, for high frequency, you will study in AC chapter, for high frequency, capacitor act as short circuit. Because there is something called capacitive reactance, which is 1 by omega C. As F will increase, the reactance will decrease. So high frequency, for a high frequency capacitor, allow them without any opposition. It's like you go. So that's why capacitor acts as a short circuit. That's why for a high frequency signal, it will just pass easily. And this signal will mix with the DC circuit, which we have in place. But again, we put a capacitor so that only AC can pass here and DC can be blocked. Now this AC which you receive this side will be enhanced from this AC, which is entering here. So if AC is entering here like this, what will come out here?
Higher amplitude.
And you can see the phase is out of phase. You can see this is out of phase.
Yeah.
Out of phase, which I will prove very soon. Why? Okay. So if plus will enter, what we get here is minus. With amplified version, minus will become. So a common emitter amplifier will act as amplifier, and the output signal is always going to be what? Out of phase with input signal. So that is what we are going to prove here. Okay. So let's write down. Again, we are supposed to write the just write the answer for what? The AC loop. You move in this loop. If you move like this, walk from here, cross it, come back. So what will the equation in this loop? V input, correct?
Yeah.
Plus IB. I mean, of course, delta we don't show. We just write as IB for the simplicity. This IB will contain everything. Let's see. Let me hide it, else it will be confusing. Okay. So DC will only go this way and AC will superimpose. So for simplicity, as NCERT has said, just write the equation. So this is VBE, right?
Yes.
As so can you write the equation? Because we know this is forward bias, this is going to be opposed, right? Now we know how to write the equation, right? So if you walk this way, what will get the equation? KVL in input side. And let's take this as plus minus for some time. So V input
Minus Q by C.
minus IBRB.
Wrote out capacitor.
No, that's high frequency, no? Short circuit.
Oh, okay.
High frequency
AC.
signal AC analysis. So if, because see, when we do the communication, we use a carrier signal, a carrier wave.
Yeah, that modulation, demodulation.
Modulation. So carrier is always high frequency.
Okay.
And we use the amplification circuit only for that carrier. Okay, because what we are transmitting is not other thing. We are transmitting carrier, actually low amplitude, high frequency. And for a high frequency, capacitor is short circuited. For high frequency, capacitor is short circuited. So much concept, right? Oh my god. Anyway, so what is the answer? V in minus IBRB minus VBE equals to 0.
Yeah.
So delta V in is how much? Can we write a delta IB into RB plus delta VB? Now, barrier potential doesn't change, right? Because VB is essentially the barrier potential or the potential across B and E effectively, right?
Yes.
So that value is very close to 0, if not exactly. It means compared to this term is negligible. That is what NCERT says. So ignoring the second term because it's very small, the delta V in is how much? Delta IB into RB. Okay.
Yes.
So we got the change in voltage as a formula. How to write the output voltage? Tell me. KVL in output side. Okay, so you're supposed to only move this way. Or you can say VCC minus ICRC. Correct?
Yes.
So V output we can write as, and you can see something. If I move like this from here, plus VCC, if I put plus minus, then how to work? Plus VCC minus ICRC equals to minus V out minus V out. I mean, okay. Yeah, let's write down the question. Let's write the KVL here. Who will tell the KVL here? VCC, ICRC minus V out equals to 0. So V out is how much? Basically VCC minus ICRC, correct? And VCC is the biasing voltage. So delta V output is how much? 0 minus delta ICRC. Big formula. I don't know how you're going to remember this. Is this done?
Yes.
Great.
Somehow we just keep ending up with different variations of V is equal to IR.
That's it. That's it. And then once you get these two answers, you're done. You have mastered transistor. So then you have V delta V output how much? Just remember like this. Delta output, you see, in the output, what we have is current and resistance. So it's easy to remember delta IC into RC. That's it. I hope this is easy to remember, right?
Yes.
Because we know what is output actually. And technically, without even studying, I can say what is delta V in? Delta IB, RB. We are done. So we now define something called voltage gain. Voltage gain. How we write AV? Because A for amplification, V for voltage, but it is called voltage gain. And it is defined as delta V out, delta V in. That's it. And V out is how much? Minus delta IC. I can do it mentally. Into RC upon delta IB RB. Is it difficult? No. So voltage gain is how much? Minus delta IC by IB, RC by RB. I hope you remember the delta IC by IB. C by becomes where? Beta AC.
Beta.
RC by RB. Very simple. And later on you will come to know this formula we can rewrite as minus beta IC. RC be replaced by the load resistance and RB by the input resistance. That's it. This is the formula for which gain?
Amplification.
Voltage gain. And because the voltage gain is negative, so the output voltage and the input voltage will be out of phase. It's negative. Positive means same phase. Okay.
Yes.
Okay.
So taking RC equals to load, this is called load, and taking RB equals to input resistance. This is the voltage gain formula. And the last formula is called power gain. Power gain. AP. P for power. A for gain. Why? A for amplification. So how we define power in physics? P equals to VI.
VI.
So power gain is defined as voltage gain into current gain.
Current gain.
So there's simple voltage gain into current gain is called power gain. And then AV we got the answer. So it is beta square AC RC by RB or minus beta square AC load upon input. So theoretically we are done. Finally. With all formula. This is the most challenging part. But it's easy to remember. I can tell you the way to remember. Delta V output is what? Delta IC into RC. And delta V input is how much? Input side we have current as IB. So write as delta IB into RB. The only difference is you have to also remember that it's a negative. Now that's difficult. Yeah. When that is, this is what you have to remember. So these are the formula. Okay. And once you remember the formula, it's easy. The last concept and the last page. Wow. So the last concept is called transistor as a switch. We know that transistor will act as a switch. When it will act as a switch? Either in saturation or cutoff region.
Yeah.
So region of operation. Yeah. So it will act as a switch means gate. You know, logic gate.
Yeah.
So it will act as a gate actually, on-off gate or not gate. Okay. So when it is in active region, it will act as amplifier. A for active, A for amplifier. When it is in saturation region or cutoff region, it will act as
not gate.
Not gate. Okay. So saturation means what? Input will be forward bias. Okay. So input is forward bias. If input is 1, output is going to be 0. So in saturation, if it is on state, in on it will act as input 1, output 0. In case of input is 0, which means low potential, output becomes high potential. How? I'll just show you. So region of working is not is R saturation and cutoff. Okay. I'll tell you what is saturation. Very simple. I'll tell you what is saturation. In any transistor, I mean, again, you have to think of common emitter only. No need to worry about other form of transistor. Parv, are you listening?
Yes, sir.
Parv is there? Gone.
No, he left.
No.
All right. So this is collector, emitter, base. This is IC, IB, IE, and this particular this is called VCE. And we take VCE as the output in this case. Okay, and if you look at the diagram here, you can see the VCE is the output, isn't it? Nothing I have taken here, right? So output is same as VCE, isn't it?
Yeah.
Because all are in parallel, no? They are in parallel. So VC is the output. That's why this is how we draw. Okay. Okay. So now, what was the input, if you remember? So output was V output we got is VCC minus ICRC. Correct?
Yeah.
Now, if V input is 0, if the input is 0, IB will be how much? 0. Input 0 means what? It is not biased. You haven't biased the input. So will you get any input current here?
No.
And if you don't get any input current, then IC is impossible.
Yes.
And if IC is impossible, it's a good thing. If IC is impossible, it means if I make a biasing, we normally do the biasing here. Let's say if I this is 5 volt. If input is 0 volt, what is the output?
Sir, emitter is at what voltage? Its emitter will be grounded here.
Yeah, emitter ground. You can think this. If I make this as 0 volt, it is what? Not biased. IC will be 0, and once IC will be 0, equals to 1 implies what? The V output is VCC, the bias voltage itself.
Yes.
So given that VC is 5 and ground, this is ground, the VC is 5 only, no?
Yeah.
So a 0 will give you 5,
5.
which get.
Not.
So how to represent the not get? A
Oh.
diode symbol with O, which means not. So a 0 will give you 1. Correct?
Yes.
If V input is not 0, I mean it is more than VC, right? So if V input, I mean, the other way of saying is if V input is, or you can see if IB is non-zero, let's say we have sufficient biasing voltage, or okay, that's fine. Input is more than B, correct? Let's say this is more than biasing voltage. So it will be in active region. Then IB will be non-zero. Hence, this implies IC will be non-zero. IC will be there. So the output will actually decrease below the 5 value, right?
Yes.
So VCC minus ICRC, and ICRC will be sufficiently large. Now, what is logic 0? A low voltage than the threshold is logic 0. Which means when you have the high input potential, the output will decrease. So it will undergo the lower threshold, which is the 0 of the logical 0.
Oh, yes.
Understood? So because V output is going to be very small than VCC, okay, the output will be below the threshold of what? Logical 1. That is, output will be 0.
Yes.
So it is again a not get, because the 1 gives you 0. So this state is called cutoff. So in the cutoff region, it will give you high output, logical 1. But in the saturation, this is called saturation. In the saturation, what you get? Logical 0, because saturation means VCE is equal to 0. This is called saturation meaning. The technical meaning of saturation is when C and E become short circuited, we call logical 0. Okay. And there's a last graph, then you can leave for the day. It is no longer night. So there is called transfer characteristic graph of common emitter configuration. This is called transfer. I don't have a space actually. Characteristic graph. V output, V input. Okay. So this will look like. Finally. So output voltage will be 0 in which region? Saturation.
Yeah.
Saturation means output is 0. Hello, hello, hello. Do you realize?
That shows high output voltage, no? The
No,
first
saturation, this is 0. This is 0, no? Output is less, no? In saturation, what happens? IC will be non-zero.
Yeah.
So as IC/RC will decrease the value, no?
Okay.
Then VCC.
Okay. The saturation region will be at the right of the graph.
Yeah, yeah.
Okay.
So this is the saturation. So this is a different graph. This is the VV. V output and V input, right?
Yeah, yeah. That was VI.
Ah, that was VI. So this is cut off. In cut off, you get the high voltage, right? High.
Yes.
And below certain, let's say less than 3 volt is, let's say this is 1 volt. So less than 1 volt is logical 0. So this is saturation. So cutoff region is called off state. Saturation is called on state. So when a transistor is on, it will act as not gate. I mean, in both cases, whether it is cutoff or saturation, the gate behavior will be what? A not gate behavior. Hello? Yes or no?
Yes, sir.
Yes, sir.
Finally. So there is a last question they will ask you. And that is, what is IC in the saturation state? Find the saturation current. So to calculate saturation current, write V output as perfect 0. And if you write the perfect 0 from this equation, what you can get? The answer?
VCC is ICRC.
So this will give you IC equals to the bias upon RC. This is the last question. Done. Finally. Okay. So one more thing which I need to add or explain is, not add, I'll just share the again screen. I'll explain there only. So in question number 69, you can see there are two terms used, the H notation, right?
Yes.
See the question number 69. Okay, so here H stands for hybrid, F for forward bias, E for emitter. O for cut off, E for emitter. So this is called the current gain for common emitter configuration. And if you know, this is nothing but beta. So HFE means beta AC. So what is HOE means? So HOE is something different. It is called output impedance. Now, what is impedance? It is resistance. What is resistance? For the output side, if you remember the dynamic resistance, if you remember,
Yeah.
common emitter, delta IC by
Delta VC.
delta CE, right? Hello.
By R, okay.
Impedance means resistance, no? Sorry, opposite, just delta V C collected to emitter voltage upon delta IC.
Yes.
So this is given to you as 25. And beta is what? Delta IC by delta IB. This is given 50. And the load impedance is given 1 kilo ohm. Okay. So I think everything is given, right? Load means RC is given, right?
Yeah.
1 kilo ohm. What they're asking? The current gain is the current gain is what? For the transistor amplifier in common emitter configuration, for load impedance of 1 kilo ohm, it's given the current gain is. Okay, anyway, yeah. So what we need is, but current gain is given 50. HF is forward current gain. But this is not part of JEE syllabus. How they ask this question? Yeah, there's a formula given, but okay, I'm just writing the formula. You have to leave this question as of now. So this is the input voltage. We write as HIE IB HRE. Okay, but we should solve this. Just a minute, let me see. This is formula given. HFE IB HOE VC. VC is the output. What is given to us? HFE and HOE. Okay. Anyway, let me solve this question. For a transistor amplifier, common emitter for load impedance, current gain, and it is output impedance. What is HOE? Just check what is HOE. Let me check. Open shorted. Okay. Just a moment.
The HO is reciprocal of output resistance.
Reciprocal of output resistance. It is like impedance.
Output
Okay,
impedance. Output impedance.
No, impedance is resistance only. So it's the inverse of impedance, right?
Yeah, that's what it says. Yeah.
Yeah, it's connectance now. Let me see the solution. This I have studied in a long time back, but this is not a regular step. Okay, let's see the other one. In 70, you can answer. 70 you can answer, right?
Yeah, emitter.
The part of transistor which is most heavy doped is emitter.
Yes.
Yeah. Let's solve this question. Yeah, this. (51) IC and VC. The output characteristic of a transistor is shown in here. When VC is 10, IC is 4, then the value beta. Beta S is what? Beta S means delta IC by delta I, right?
Yeah.
And VC is 10. Okay, here. So you can choose any two line.
Yeah.
Whose value you can understand. I think these two line value you can understand, right? These two value. This is 2 and 4, no? So delta IC is 4, 2 only, right? What is delta IC? Delta IC is 2, isn't it?
Yeah, 4 minus 2.
2 milliampere. And delta IB is how much? It is, I think.
So delta is in microampere.
No, IC is in milli.
That is
IC will be in milli.
Yeah.
And what about the IB? It's micro. So this is, I think, I don't know what is given. Which line is given? 10, 20, 30. Okay, it is again the same, no? 10 to 30, which is 20
microampere.
3.
Yeah.
100 times. It's 100 like that.
100.
What is the answer given? You can check. You should mention the answer. Just check the answer.
So what was the question number?
Question number was what was the question number? Not here.
Doing topic 3. हाँ.
Topic 3.
नहीं sorry.
Topic 2 ना?
हाँ 2 में होगा.
Somewhere here.
Yeah, I got it. It's 51.
Yeah, 51. What is the answer?
1 second. I'm looking for solutions. 150.
Why? Why it is 150?
Delta IC they have taken. Delta IB they have taken 30 minus 20. And delta IC 4.5 minus 3.
4.5. So, I think the diagram which they have put
the graph
here. Yeah, graph is not accurate. I mean, graph should be accurate anyway. You know the process, right?
Yeah.
So come to this question. I mean, these are just formula. Come back here. Yeah, this question. I think you can answer this question. (56). That is looks like a difficult question. Hopefully. 56. This is what we drew, no? While deriving the formula.
Drew this complete diagram.
Exactly same diagram, no? Yeah. So this is exactly from NCERT. So transistor will go saturation when IC is VCC by RC, and VCC is given. I think RC is given. You can get the IC. Once you get the IC, you can get the beta from. Then you can get the IB also, right? Two-step process. For saturation, what we write? VCC minus IC RC equals to 0. So VCC by RC is the IC.
IC.
Everything is given to you. VCC is how much? 5
volts.
RC is 1000.
1000 ohm.
So 5 milliampere. And beta is given. So beta means IC by IB. So IB will be how much? 5 milliampere by beta, which is 200. So this we can write as 25 by 1000, right? Microampere.
Yes.
So IB is 25 microampere. So we have two options, A or C. We have to check the other part. And other part is the minimum base current and the input voltage at which transistor will go saturation. What is the input voltage formula? The input is, if you remember,
IBRB minus VBE.
Minus VBE. I think VBE is given, no? IB we got 25 microampere.
Yes.
RB is 100 kilo, which means 10 power 5, right?
10 raised to 5.
5. So minus 6, this 2.5. Minus 0.1.
Yeah, VB is given 0.1.
1. Oh, it's addition. It's not. It's a plus actually.
अच्छा sorry, KVL में एक साइड पे लिखा. हाँ, VB प्लस आएगा.
Plus है. तो 3.5 आ गया ना? ये आंसर आ गया.
हाँ.
अच्छा, exactly उस पे बेस था नहीं, सोचो. मतलब
हाँ।
पूरा डेरिवेशन पे ही बेस्ड है ये।
हाँ
Got it? How to solve?
yes
And 57 is that formula. You can just see 57. It is that formula. We have just done this question. So current gain, voltage gain, power gain, right?
yeah
So voltage gain, current gain. First, I have the voltage gain. So voltage gain is what? We know the answer. Voltage gain is beta times RL by RB, right? The load upon input.
load upon
So that's the answer. Beta. The first is correct. And current gain is delta IC by delta IB. We know this answer.
yeah
Common emitter, and power gain is beta square. Just multiply these two, right?
yes
See, they haven't written beta, they have written delta IC by delta IB for that reason, which is beta itself, right? So option is D, correct? Just check.
yes
So all these tough questions we can do also. Okay. Solve question 53. Just check the question 53. 53. Practice. Power gain of 60 decibel. You know power gain when we express in decibel? When it is logarithmic.
oh
Just like the loudness definition, right?
yeah
So 60 decibel. So anyway, this we have to use a formula itself. What is the formula? Power gain equals to beta square, the RL by R.
dynamic resistance
But they have given 60 decibel. I think we should convert into. Yeah, this is not. We have converted into some log definition. How they write it? ln log base 10. Maybe 60. Is 60. So log AP is 60. Decibel means how much bell? Some value. I don't know what is the exact, I mean, relation. I need to know this. Just a minute. Power gain dB formula. Oh, it is 10 log output power upon input power. I think we can decibel, we can convert into 6 only. It looks like 10 power 6, I think. Because decibel means how much bell? 6 bell. So AP is how much? 10 power 6.
yes
And this is equal to how much? Beta square into
load resistance is 10 kilo
10 kilo upon 100, right?
100
314,422
2.
This is 4. So beta is 2, right?
Yes.
100. A option. You have to be careful.
Sir, if these derivation-based questions are coming in mains, then what should we expect in advance?
Advanced will have the same level. Don't worry.
Okay.
The reason is the advanced is going for the first time. No? So
Hmm.
first time it will be slow only. Relax.
Okay.
Let me tell you, in some chapter, mains is difficult than advanced.
Oh.
Okay. Because see what they believe that okay, those who are preparing for JEE will not study this chapter much. But even if you only prepare for boards, also you can't solve this question.
Oh.
So you anyway you need to study this in deep only.
Hmm.
Solve 54. It's good we are solving. At least you're getting some idea how to solve. Just read the question number 54. We are almost done with all questions. 53 understood how to solve. Convert decibel into bell, get the power gain, use the formula, get the current gain. Simple. (54) NPN transistor is used in common emitter configuration as an amplifier with 1 kilo and load resistance.
It's probably ohm printing mistake.
Probably 1 kilo ohm of load resistance. Signal voltage of 10 millivolt is applied across the base emitter. This produces a 3 milliampere change in the collector current. So delta IC is given.
The signal voltage is which one?
V input, VIN.
The AC wala?
AC.
Okay.
Signal voltage matlab ki AC, that's it.
Okay.
And this produces 3 milliampere change in collector current. So delta IC is 3 MA. And 15 1/4 ampere change in the base current. I think 15 micro. It's so much printing mistake. 15 microampere change in the base current. Okay. Delta IB is how much? 15 micro.
Microampere.
It's not 1/4, it's a micro. I mean, it's typo. So the input resistance and voltage gain are. I think this can be solved. So beta is given, no?
Yeah, beta is given.
How much? Delta IC by delta IB. This is AC only, right?
Yeah, 200.
So beta you got 200.
And
luckily there's only one answer. Anyway, but let's solve the other part. The input resistance is how much? But they're asking voltage gain, not the current gain. So voltage gain is what? Minus beta load upon input.
And input is delta.
We need to find this, and this is given. This you got, and this you have to find. So first we have to find the voltage gain. So voltage gain is how much? What is the load resistance?
Load is 1 kilo.
Output voltage is defined as ICR load. Or delta V output is how much? Delta IC RL.
Yeah,
Delta IC is how much given? 3 milliampere.
3 milliampere.
So 3 10 power minus 3. And RL is 1 kilo, right?
Yeah.
So delta V is 3 actually. 3 volt. This is delta V. And delta V input we can say is 10 millivolt. So voltage gain is how much? 3 by 10 milli. Which is how much? 300, no? So voltage gain is 300. B or D option. But now we can answer the other part because voltage gain is 300. So beta 3 milli 15 micro.
Beta was 200.
Beta got 200, na? So okay, 200 into RL is 1 kilo ohm upon R. 0.67, right? Kilo ohm.
Yes.
B answer. Are you getting how things are happening?
Yeah.
The signal voltage itself is delta V input.
Okay. Yes.
I mean, difficult to interpret as the first time. But anyway, we are solving. That's why we are solving every question. Hopefully, it will help. And now you can see the 59th question. In the 59th question, it's common emitter, NPN. The phase difference, we know the answer is 180. Okay.
Yeah. Emitter, yes, 180.
It's common emitter. In common base, it is same.
So common base case, have you written in the notes somewhere?
You can derive it by differentiating the input and output formula.
Okay.
I think this is one more question which we should look for. 61. A realistic graph depicting the variation of the reciprocal of the input resistance in an input characteristic measurement in common emitter transistor configuration is. You know what is common emitter? You know it. What is input characteristic graph generally? IV graph is a typical forward bias graph, right?
Yeah.
But what they are plotting here?
1 by R versus
1 by R versus V. Correct? And input resistance we know is how much? Delta V by delta I. So inverse means what? Delta I by delta V.
I by delta.
Versus V. This is what you have to plot. So it is like we have to plot the slope actually. Like slope versus V.
Yeah.
So what is the slope of this graph? 0 first. In the beginning, slope is 0.
It's increasing.
So graph must begin from 0 somewhere. So you can see before the cutoff, this is 0 till here, no?
Yeah.
So which graph is having 0 value in the beginning? Only B graph.
Only B. Oh.
You can check the answer. Tell me the answer if it is correct or not. Just tell me the answer. Hmm.
61. 61, no? 61, they're showing C.
Inverse of ratio delta by delta V means slope. So slope versus V. So when V is 0, slope is also 0.
It's probably a printing mistake because in their solution graph, if they're starting from 0.
Yeah, graph will start from 0 for sure.
Yeah, their solution starts from 0, but here the C option starting from 10.
10. Quite possible that may be wrong. Because we have to only think common sense, like delta by delta V slope. And if you look at the slope, so in the beginning till the barrier potential, it is 0 slope, right?
Yeah.
So the graph should have been in fact like this. And then like this. Why? Because when it is almost a straight line later on.
Yeah.
So almost it's constant.
Almost one.
Because slope remains constant, no? So you can see this is asymptotic graph, which is also meaningful. Because slope will not increase forever, no? It will become constant. I think this is B only. Okay.
Yes.
Almost done, or any other question you can see? Something, okay, not this is done, almost done. We are at the bottom. Let's think of the these are from experiment. I need to also see whether I know or not. Try this question, 63 and 64. This is from the, I think, experiment. Let's do it. An unknown transistor needs to be identified as NPN or PNP. A multimeter with positive negative terminals is used to measure resistance between the different terminals of the transistor. If terminal 2 is the base of transistor, then which of the following is correct for PNP? So for PNP transistor, the 2 is base. And base current is very small, which means the resistance in the base to emitter side should be very high. High resistance. Correct?
Makes sense.
And we know that this is forward biased. So we have to plus this minus. And this is reverse bias. So this is, sorry, this is P, N, P. So to make forward bias, you have to put a minus and here a plus and here, right? Yeah, this is forward bias. And C is P. So this is minus, reverse bias. This is what we know. So if terminal 2 is the base, then which of the following is correct for PNP? So terminal 2 must be negative.
Yeah, option C. C and D.
And resistance high. Yeah, correct.
Terminal 1 must be positive.
So if this is
There will be
case,
terminal.
no, I think emitter is always taken as terminal 1, I think. I think so. No, this is 3. If we take emitter as terminal 1, then it must be positive. Then C becomes the right answer.
Yeah.
Just check, then I'll confirm the theory. I mean, I think then EBC will have the reading 1 to 3. From here I can deduce. I don't know. Just check the answer.
Actually, I had a practical experiment of this identifying PNP or NPN.
Oh, great. So you can tell me, no?
नहीं तभी कुछ समझा नहीं था कि hadn't studied ना transistors and all.
In fact, I never did the experiment, so I don't know. So I am relying on the fact that okay, maybe this is like a theory. I can guess from the theory only. Just check.
C3 is C.
C, na?
Yeah, terminal 1 is emitter, 2 is base, and 3 is collector.
Yeah, so we have done. We have cracked the question. Okay. So this is how we should do. Good. Then solve the 64. So I think 1, 2, 3 is like A, B, C, right? The emitter must be A, B, and C.
Names. Yeah, they are just names.
Yeah.
Yeah, it's not necessary.
Oh, not necessary. Yeah. I don't know. Correct. Not necessary. Let's read and then we'll try to understand this part. An NPN transistor has 3 leads A, B, C. Connecting B and C by moist finger. Moist finger means you make a connecting.
Yeah.
So if you short circuit B and C, yeah, we are making short circuit, right? Then A is positive lead of the emitter. Okay. And C to the negative lead of emitter. One finds large deflection. Then A, B, and C refers to. So large deflection means large current.
Large current.
And you are making B and C short circuit. It must be saturation region, I think. Because if you make the short circuit to the input side, there is no current. But if you short circuit the output side, you will have the large current. The saturation region, right?
Yeah, not gate wala.
Not gate wala. So in saturation region, B and C must become the collector and emitter.
Yes.
A must be the base. So A, B, C, and A is positive lead of emitter, and C is negative lead of emitter.
Base must be forward biased in this, right? So
I don't know. Still, I don't know. Okay, it's N pin. Let me draw and try to understand this. N. NPN. And what is said? Connecting B and C by moist finger and A to the positive lead of an emitter and C to the negative lead of the emitter. One finds large deflection. Okay, positive, A to positive and C to negative. I think it looks like this, large current here. And what they are doing is they're making B and C.
They're sorting B and C.
Sorting B and C.
But we established na ki if we are sorting, then one should be emitter and one should be collector.
Yeah. A large current with shorting means it should not be at least input, it must be output side. But we don't know which configuration is this. Is it common emitter configuration or common base? Do we really know this? So is there any theory as per the experiment that we should do this way?
Not really sure.
Can you just read the solution and tell me? Then I can infer something from there, hopefully.
No, it's just given in the given question. A, B, and C refer to base, collector, and emitter respectively. Nothing
Base
else.
collector. Okay, C the answer, right?
Hmm.
Okay, let's infer from here. Let's create the theory from here. Okay, so B and C are short circuited.
So that was saturation region.
So large current means saturation region. For saturation, B and C must be
Collector emitter.
but it's saying
We are not
collector.
sure which is B and which is C.
Then A, B, C refers to base. Collector and emitter. Yeah, so A become base, no?
Yeah,
That
A was
is
base. We are just unsure about collector emitter, but I guess
Hmm.
that we can infer from which sign we are connecting to the ammeter.
Yeah. So emitter is come on. A to the positive lead. Yeah, A is positive means it's forward bias.
Yes,
So now this confirm now.
A is base.
A is the base.
And C
And
to
if
the
A is the base, then negative is, and C must be the emitter. And B must be collector, right? Because C is negative, no? It means C must be here. Because A is positive, C must be negative because this is forward bias.
yeah.
So C is emitter, no?
Yes.
Base collector. Okay, slightly difficult, but good. Okay. Anyway, I'm solving also for the first time. This question I never solved. I left. Okay, I thought this is experiment, so must be doing in a school lab.
Oh,
Okay. So I think every tough question you have seen, right? From transistor part. Done. 63, 64 done. All are done, I think. Except 69, I think everything is done, right? Almost. So we have covered almost everything.
more experimental one.
Yeah. So what I will say is that, okay, just solve the remaining part. Practice once again. And see, the simple rule is in JEE-Mains, they will ask similar question if they ask again. So even if you know the process that how they have solved, that is sufficient. You can just proceed in the same fashion. You get the answer. Okay. So now I can stop. All right.